All right, welcome everyone to the third edition of the workshop on reinforcement learning for energy management in buildings and cities. My name is Zoltan Nagy. I'm faculty at UT Austin, and I have the pleasure to welcome you to this session, which is organized in hybrid mode. First, some issues that are not relevant to the technical part. There is some breakfast presented, organized in the breakfast room for those of you who are in person. There will be also some lunch after the session, I think around noon. So please go ahead and grab some of those things while you're enjoying the conference. So I'm obviously not alone. There's a bunch of people in the background that you'll hear today and that are working tirelessly to organize this. In particular, the technical program folks, Kuldeep, Matthias, Yashin, who organized the program, made sure that we have a solid work combination of excellent keynotes and also some really good papers that are being presented. And so hopefully we'll have a good discussion and move forward and discuss the big problems that we're all having in this field. And why we're organizing RLEM, it's a central problem of building control. And what we find is that, or at least what happened to those of us who thought we should put this program together, is a lot of the developments are happening in different fields. Some of the folks, working more on the building side, getting more and more into control over the past years. And then those working in the machine learning and advanced and intelligent artificial intelligence are getting into buildings, sort of an application. So there's a confluence for that, and so we thought it would be good to provide a sort of a forum to discuss, progress in this direction. What are the big challenges? Where people should go? What should we study? Where should what are the big problems that we should tackle? And so this is why we have this forum, and so I'm excited to see what's going to happen today. This is not the first time we're doing this. In fact, it's the third time. Started in 2020, which was virtual in Japan. And we had about 50 or so participants, and then same last year in Portugal, around 40 or so participants, which was also in hybrid mode. And I think this year we also had about 40 registrations, so hopefully we get a similar number as the day progresses and then people start trickling in moving forward. The program for today, as soon as I'm done speaking, we have a first keynote by Troy, who is joining us from Australia today. Then we have a technical session of 3 papers, I believe, about 10 minutes each. Then a second keynote by Gregor, who is joining from Colorado. Another technical session of 2 papers. And then at the end, this is where we will pull back the keynote speakers for a panel discussion. But I want you to think of this not necessarily as a one-way street where Troy and Gregor keep speaking, which they will, but it's also a good idea to speak up and share your thoughts and then create a bit of a dialogue around the ideas that are discussed. You may disagree, you may agree, or you may have other thoughts. Ideally, this goes beyond the typical academic presentation where there's a speaker and then there's 2 questions at the end and everybody claps. Hopefully we have a bit of a discussion where we can share some thoughts. The program is pretty packed, timely, but there is time for discussion at the end, so we may cut some things short as we move forward in the interest of keeping roughly our time schedule, but then we'll have time in that over half-hour panel discussion part where we can pull out those questions. So make notes so you don't forget your questions. And then, we will come back to those definitely. Okay, so with that, I would like to introduce our first keynote speaker, Troy Harvey. Troy is the CEO and co-founder of PassiveLogic. He's the creator of the first platform for generalized autonomy. As the architect of quantum digital twin standard and deep physics AI engine, his empathic, systems-oriented approach to technology development is transforming the way we control systems and equipment. Optimizing buildings, cities, and other control systems is the clearest opportunity Troy sees to contribute to the world's most pressing climate challenges. Troy, I'll stop sharing my screen, and while you're setting up, I will say that Troy also hired 2 people in the last month or so who were in this very same room. So from this audience, which makes us, of course, very proud, and hopefully they can live up to the expectations that you have to this community. But things happen, so welcome, Troy, and take it away.
Yeah, let's see if we can get this up. Is this working for everybody?
I can see it.
Okay.
How's the room?
Well,
yes.
awesome.
Yeah.
I am in right now in Perth. I'm not normally in Australia, but Perth does have the interesting distinction of being the furthest city away from any other human inhabited city. I think it's a 5-hour flight to just about any other city. So the internet hopefully will keep up with us and work out. I'm going to go through this. It's a bit of a big presentation in a short period of time. So just kind of hold on tight. But let me just give you a sense of who PassiveLogic is. I think it's been a really fun journey for me. Building up a team today. We're about 100 researchers and engineers and team members, and we're looking to actually double that over the next year. I think this probably makes us the largest advanced controls R&D team in the world today. And we're backed by a lot of big players, from technology players like NVIDIA to big building owners like Brookfield, and working with national labs and the Department of Energy. So that, I think, represents something that's happening at the zeitgeist right now in the marketplace of how do we really go and solve some of these big problems. I'm not going to, because of time, go into this whole big topic of ESG, but I want to give you an outline. What do I see as some of the big market challenges? And then we'll drop into what are autonomous buildings, what is generalized autonomy, talk a bit about the PassiveLogic approach, some of our work in compiler technology with the Swift language, and then getting real. I think it's important to pop out of the academic stuff and say, how are we going to do this and make AI for the masses? So here's the core problem. Today, smart buildings, people use this term, they're not actually smart, right? That's a euphemism for connected. And I think of these technologies when I was a kid. There was this late night TV commercial for the clapper, and you clap your hands and the lights would go on, you clap your hands and the lights would go off. Most of this stuff today is just the clapper for your phone, right? It's not actually smart. It's not doing anything more than that. And what we're really missing is an organizing intelligence for all these things we want to do within buildings. And today the marketplace looks like this, that if you look at the market stats, building automation lives above 100,000 square feet in the commercial building space, and that's 3% of commercial buildings. So you got all these big companies that are all competing over 3%, and then there's 97% of the commercial buildings, and then there's multifamily residential and industrial and so forth. So we have these two sides of the market, one where BMS doesn't actually work very well, and the other where BMS doesn't exist. So how do we actually address the whole marketplace? And there's this big challenge that I see, that really what's interesting about this market is we actually start with all the information at the beginning of the architecture process, and through the process we lose it all. And then once we install controls and we're commissioning them and maintaining them, then the client calls and it's like, hey, it doesn't work. And yet part of the real problem was that we lost the information we already had. BIM as a topic doesn't work past mid-construction. So we design all these things in Revit or ArchiCAD, and then somewhere mid-construction, that information diverges from reality. And that's a huge problem in terms of our building lifecycle, what's actually happening in buildings. And then when we look at the actual installation of these systems, when I go around the world to all these different installers of automation or distributors of automation goods, the typical distributor will tell me that they have 500 contracting companies they work with, and maybe 5 can install a BMS from one of the big BMS providers. because of the programming requirements, the commissioning requirements, engineering. It's just too much for boiler, Bob, and HVAC, Harry. So, and that labor, more importantly, it's getting rarer. So the average age of a programmer for BMS is in their mid-50s, and there's very few 20 and 30-year-olds entering that field. So they've got a big challenge. How do they modernize themselves, and how do they also democratize BMS to the real people that are installing? One of the things that's interesting, you know, I was in Sydney yesterday, and the discussion between all these REITs, these big building owners, was like, oh, gotta have data, but they don't know why they have to have this data. And it turns out they really don't, right? Data is not very useful. This is sort of a myth that's promulgated by the Googles and the Facebooks whose business is data. For most of us, data is not very valuable. What people are going to put money down on is action. How do we run our buildings? Not, you know, like, what do I do with a big pool of data about my building? The other big challenge, if you look at building automation in the real world, it ends up looking like this. Is a diagram from a popular automation newsletter. And we're never going to get there this way if we have to staple together 30, 40 different point solutions. There's only a few buildings in the world that could possibly put together the technical teams to be able to do this. So this isn't a way we're going to get there. Now, to this audience, I think the fundamental problem is this. What we don't really recognize as an industry is buildings are actually the most complex systems by far than anything else people make. So an autonomous vehicle maybe has 50, maybe 100 sensors and 3 controllables, right? It can steer, it can brake, and accelerate. Buildings start with this huge state complexity, even at a few thousand sensors, and they get up to 500,000 or more IO points in your biggest building. So there's nothing else that compares to that. And the tools that we have to manage that complexity are just incapable of actually matching up with the challenge, right? So I think we need to really start as an industry thinking about buildings. This is the world's most interesting robotics challenge we have. But it has another problem, which, unlike the Tesla that is, you know, 100-ish sensors and 3 controllables, and you can program once, every building's a different topology, right? So we can't just use a autonomous platform and apply it to buildings. Buildings need something different. They really need generalized autonomy in order to attack this problem, because every building's got a different architecture, systems, equipment, topology, engineering, location, and so forth. So there's a lot of really interesting challenges in buildings. And the way that we see it at PassiveLogic is the only way we're going to really approach this is full autonomy. So our goals are fully generalized autonomy, any system, any topology, any application. It has to be built on existential knowledge, no training periods, and we'll talk about why. And it has to be self-serve. We got to fit that giant problem of how are we going to get to all the buildings in the world? It's got to be democratizable. The way we see it is like this, you know, that all we have around the building is kind of all the other solutions, right? So we think of, you know, Tesla can have vehicles. What we're really interested in is like everything else, and it tends to congregate around buildings. So let's talk about what autonomy looks like and what does that mean. So the first concept that I want to introduce is that first, the degree of autonomy is separate from the implementation details. We're going to be talking about a lot of different papers, a lot of different implementations, whether it's AI, some kinds of machine learning, model predictive control. These are technologies, not solutions, and they all fit within this rubric in different ways. So, you know, when we look at algorithmic control, this is level 0 autonomy. This is like manual control. This is like cruise control in your car. It's most likely in buildings and cars to be PID that's running those things, right? Level 1 autonomy, we start with this notion of, you know, again, the degree of autonomy is separate from solution quality. So there are solutions out there that are doing things like system tuning, right? Whether it's AI or MPC. There are solutions out there that are adaptive runtimes, meaning that they're a little bit you're still level 1. You're doing adaptivity. You still have dumb controls. You're still just tweaking and tuning, but it's the degree to which you're doing it in a more or less real-time basis. Level 2 would be sequence generation assist, right? This is so key concept here is we talk a lot about control loops, but loops are actually a small part of the overall set and sequence of operation. So sequence generation assist would be if I have some kind of system that can help generate statically during engineering, pre-runtime, what are all those sequences without me having to code them myself. Getting to the level 4 autonomy is actually where things get really interesting. This is where buildings on their own are making their own sequences in real time to adjust for the dynamics in their building. And then level 5 is really what our company is focused on. This is real-time sequencing happening in the building at the edge, but not just for a system, but for the systems of systems problem we have in buildings. So that's kind of how we think of this levels of autonomy. And so internally, the way that we talk about autonomous buildings is fully autonomous, making real-time control decisions at the edge is full level 5, self-federating of all of those sensors and IoT, doing that data fusion. Controls that actually know what buildings are. We can't actually solve these problems unless building controls understand what buildings are. And you can do that using physics-based digital twins that understand the underlying physics of the buildings and the equipment, the systems, and the people. And using those, we can be aware of the future. We can say, hey, if I make these N choices, what is each one of those controlled decisions? What is the outcome? And how do I compare it? And if that outcome's an hour from now, 6 hours, 12 hours, that I can get some time awareness as well as the degree of control, immediate control awareness. But it also has to be introspective. So you can't just like roll the dice on millions of options and pick the best one. You still don't know anything. So introspection allows you to then reason about what you did and communicate it back and be able to answer some of these bigger questions that are going on in buildings. And finally, we talk about smart cities, but of course you can't have smart cities unless you have smart buildings, right? And so you really need to solve this problem in order to unlock things like smart grids and peer-to-peer energy networks. So that's how we think about autonomous buildings. I want to present a framework for generalized autonomy, and then we'll talk about how we solve it as a company. So everybody, I think, is familiar with this point in the world today of vehicle autonomy. This is single-purpose autonomy. A Tesla is going to just be a Tesla. It's not going to be a Honda or a Nissan. It's certainly not going to be an airplane or a helicopter. You can train it once, and then you have assembly line deployment. But in buildings, like we said, we have this bigger challenge, right? And so that autonomous control is just one piece of the bigger puzzle that we have to solve in this every application is unique world. So the first thing that we have to solve is autonomous environmental assessment. What is the environment we're in? What are the key requirements? What are my values? What are the ground truths? What are the targets that I'm trying to hit? How do I meta program myself for this application? How do I train that meta programming to meet this application's need? And then I want to sort of like take a moment and do a little sidebar here, because one of the interesting challenges here, this is a big area of, if you took this from a deep learning perspective in a traditional deep learning approach, you would have to train in numbers of models, several dozen models to attack different problems, right? How are you going to do control? How are you going to do environmental assessment? How are you going to meta program for your ability to IO map and do fault detection and analytics and your semantic knowledge graphs? So this would be a big lift in a pure deep learning world. Autonomous control, right? This is the core thing that a Tesla does, but in buildings, it's a bigger systems of systems problem. Automatic data fusion of our sensors, automatic insight learning, and then this introspection. How do we, in an autonomous way, be able to introspect, self-introspect, and understand our own purposes as we operate? So within that, we see several key questions in control theory. So observability, controllability and stability. So observability, I'm not going to go deeply into the notion of emergence and entropy, but observability is the inverse of entropy. Controllability is the inverse of emergence. And stability is the degree to which our model matches our system. So just briefly sidebarring on the notion of emergence and entropy here. That first, emergence in a system is the outcome of the information and ontological entropy in that system. And the first thing, I'm just gonna like kind of put this one to the side for now and just say, the main thing that we do to address this is to use digital twins to both give us better observability and a better ontological notion of what's going on in the building. This is kind of a deep topic, we don't have time for it. So I want to like head to this notion of stability because this is about reinforcement learning. And some of the big questions here are, what is the degree to which the system's knowable? What is the degree to which the a priori laws of that control system are fully understood? And then how do we adapt while we're operating to the things that we don't know? And that's the topic of this whole gathering. So just kind of talking about the dimensions of control and how where things the different approaches to control along a spectrum of reactivity to future. And what I'm going to focus in is not on this older stuff, but in this newer space of when we think about more future-centric control, it ranges from probabilistic futures to deterministic futures. So the factors that we're really interested in are these four factors: state estimation, speed, ontological awareness, and certainty divergence. And if we think about some of these notions in control that have been typically used in a lot of research, you've got statistical methods, you have offline MPC, you have online MPC, and what we're really focused on is this, what we're calling future forward control. And I'll make the distinction here that what we're interested in is, on one end, if we had model predictive control, what would model deterministic control be? How could we talk about things that are less probabilistic and more deterministic? And so I'm going to provide a theorem here that says, if we want high certainty future forward control, what are those controlling factors in certainty? And these four factors, as your state estimation becomes instantly fast and your time to generating the new control path becomes infinitely short, and your path divergence becomes infinitely small, and your ontological awareness becomes fully understood, then your futures become deterministic, not predictive. So I think we set this regression point, like way out in the future, this is what a deterministic instead of a predictive control system would look like. And for us, when we look at these factors, the things that are most important to us in how we weigh, where do we put our energy? Well, the most important thing is state estimation, the degree to which you can shorten the time from what is my current state of my building to estimating that within my model allows me to make those decisions that are very real time. And therefore, I don't have this sort of divergence between what might be happening in the building and what might be happening in my model. And then that follows on to the ability to have a heuristic that pathfinds my control path as quickly as I can. So those two together are the most important. The least important is actually certainty divergence, because that only really governs how much I'm going to do these trade-offs over time. So if I have some divergence an hour or 6 hours from now that makes it 80% true, well, I can handle a lot of that in a discount rate that still gives me immediate control without a lot of trade-offs. So that's the least important topic. So we've been focusing a lot on the speed of state estimation, the speed of control path generation. And I want to just sort of present this, and I'll come back to it. But It's important to understand that, yeah, we can crank up the speed on things, and it's not just that we get faster. Sometimes hitting a certain level of speed is a whole new set of possibilities. So no matter how fast your race car goes, right, it's not going to hit escape velocity. Once you hit escape velocity, new things are now possible. So I want to come back to that because this is an important notion in terms of how do you meet those two terms of certainty. So putting this into context of some of the things that we're doing at PassiveLogic, or maybe a lot of the things we're doing PassiveLogic. So many years ago, when we started PassiveLogic, I said to the team, we're not going to invent anything that we don't need to. And then we went down the rabbit hole of trying to solve this problem from the top down and said, this is how it should work. And then we said, boy, the technology doesn't exist. And we went through a series of reinventing everything from the products to the software, to the digital twin, to the AI frameworks, all the way down to the compiler. So it's been a bit of a fun ride to take on something this ambitious, but it's all been for purpose to start from what are the needs, and then how do we make it happen? So I'll break down some of these. First, the digital twin. So digital twins are a topic that are thrown around. I think that they mean different things to different people. So for us, digital twins are the language of purpose. We developed this digital twin language called Quantum that is really a language for defining autonomous systems. And we opened this up as a standard that anybody can use earlier this year. And it has multiple goals. It is the AI. It is also a single standard we can take from manufacturing all the way through the maintenance and management of buildings. And the key notion here in Quantum that's really distinct from how we've thought of things like haystack and brick, which are maybe labeling semantics or other types of lightweight digital twins, is what we're really interested in is what we would call technological existentialism. Like, what is it to be a pump in the universe? And how would you know as an autonomous system what to do with a pump, right? And so there's these 5 concepts here. What actors, what are your role? What's your role in a universe? What's your role in a system? Turns out no matter what kind of systems we looked at in the world, whether they're manufacturing or process control or HVAC or energy, we only found 9 actors. Actors then are defined by their behaviors and their properties. The behaviors are the things you do, and the properties are the things you are. And what do you do them to? You do them to quanta. Quanta are the currency of interchange. And so when we break this down, from Quantum, what we wanted to do from a platform is we wanted one single source of truth that was inferenceable like a neural net, queryable like a database, introspectable like a semantic graph, and callable like an API. And this is important in terms of what we're trying to solve, because in deep learning, you typically have a set of inputs and a set of outputs. And for each task, you're going to train a different model with a different set of inputs and different set of outputs. So this is a multi-perspective network graph neural net that you can introspect the question and introspect where you want to answer to, and you can inference across that line from each dimension. And for each dimension that you're learning on, you're actually reinforcing all the other dimensions that can be inferenced from different points of view. So this really helps the larger context of what we're trying to solve. It's also designed to be work the way the real world works, that you don't need to make models of everything. You just need to say, make a model of a ball valve, and you can train that to be a ball valve that here's a Belimo ball valve, but that's not one monolithic equipment, it's composable. So there's a ball valve body, there's an actuator, there's a control interface, there's maybe some sensors. And it turns out Belimo maybe sells thousands of these different valves, but they're only made up of 7 valve bodies, 6 actuators, 5 different control interfaces, and it's just composition of how you rearrange those things. And then that same actuator may be used by somebody else, and you can form assemblies. So just like the real world, we're composable. And so it's a different kind of network than you might have in a non-typed deep learning net. This is fully typed actors and fully typed quanta, or the interchanges, so that the nodes and the edges are all typed. And that allows us to compose. And for an actor, each actor then has internally those graphs that are normalized across all different physics domains. So if I'm interested in introspecting inline resistance, it doesn't matter if it's hydronic or air or electrical or even a mechanical device. Quantum also has multiple levels of abstraction and dispatch. So at the end of the day, when we're inferencing, we're flattening these graphs and computing them. But unlike, say, TensorFlow or PyTorch, we're not stuck at the flattened graph level. We're able to pop up to the behavior level and dispatch that, or pop up to the component or the equipment or subsystem level. And this is really important because if you look at the code base for TensorFlow, 95% of the code base is actually trying to do these fusions between, as it's watching the graph pass by, it's looking for captured like 2 sets of operators, 3 sets of operators, 4 sets of operators. What can it fuse to make efficient dispatch? Because this is hierarchical, you can just choose to pop up to another level and dispatch at a more efficient level if you want to. Like many of the things I'm going to talk about here at PassiveLogic, we've focused on usability. So we've made a tool called Quantum Creator, and this allows you to make your own digital twins, build up the physics graph. You have a physics editor, and you could train them right in the tool. Okay, so that gives you a little bit of context about digital twins. So how do we use that in a control context? So the first thing I've mentioned about deep learning, that we have this problem in deep learning, and it's that every building's unique, right? So you're not going to learn across all buildings and apply it to any building. And no one model is going to, fit all. And your data set, by definition, is a 1-year data set to get, one data set, right? And so if you want 1,000 data sets to get a certain, level of certainty, that's 1,000 years. So this isn't going to work, right? So we can't afford the raw training of deep learning. So what we've come up with at PassiveLogic is this notion of instinct, right? So there's post-learning and then there's pre-learning. And pre-learning is this notion of instinct, that training these subgraphs of a digital twin of a component that can be trained individually. In fact, they could be trained generically. It doesn't have to be trained per manufacturer. And then later a user is going to do composition to define a system, define a building, define the IoT structure. And what they've done is taken these pre-trained components, these subgraphs, and then turned it into a macro graph that then is this generatively pre-trained model. And then during our commissioning process, it gives us an opportunity to model optimize that model as a whole, but largely it's all got its inherent notions that it's inherited from the subgraphs of the components. Between the inferencing approach, this multi-perspective inferencing, as well as the workflow, we're able to do all 3 notions of inferencing. So we can abduct from our observations into the hypothesis of the world. We can deduct from that world to simulate where our futures are going, come up with predictions. And then we can make those control actions and induct to infer the rest of the world that doesn't have direct sensory data streaming from it. So this is sort of a crucial notion as a framework for how we think of things. So getting back to that rocket ship versus race car, achieving escape velocity here. So PassiveLogic, as of this spring, our engine compared to Energy Plus and GenOp is about 6-7 orders of magnitude faster at getting to these solutions. Now, obviously, Energy Plus and GenOp are not capable of all the things we're talking about. So we have to take a subset. This is a learning on a model, given the data of that model, to reconstruct what is the shape of that building. So that's a problem that they both can work on, where Quantum's interested in a much bigger superset of problems, but it's instructive to what we're trying to solve here. Is having very, very fast solutions that allow us to do this in real time. So really shortening up state estimation and getting that control path generation. So when we put it together, it ends up looking like this, where we have this, there's no algorithmic layer here. There's no PID. There's no, there's nothing in the middle to cause more entropy, where we have fast state estimation that is running that physical model. On top of that physical model, we have a non-model based pathfinder that is generating the control paths that then apply it to the system. The sensors come back, and we have learning functions that keep the model in line. And as we go off start to diverge from our predicted futures, we restart the model and start all over again without this algorithmic layer. So that gives us high certainty, low entropy, and really fast enough to control the system without another layer in the middle. It also allows us to meta program what we're really interested in, systems of systems, right? We can't really address all these micro and macro states unless you're actually solving the building as a whole system all at once, and then applying those paths to all the systems all in coordination. That digital twin runs on a platform that's in the building. So we say autonomous building, that has an implication. It means it's autonomous. It can't be doing this from the cloud. It's not resilient enough. So this is solving that right on-prem, and it's meant to be scalable. So we've developed this as a scalable solution that as you go from a small building to a large building, you get more controllers, you get more compute. That compute all self-federates. That self-federation chooses a leader. That leader then dispatches all of the AI compute across the cluster of controllers within the building. That system is using an AI engine for ensemble. So there's no one method or algorithm that's going to solve all problems here. And so we built this edge engine to be able to dispatch these problems that are mixed. So agent-based graphs, multi-dispatch, chaining and seeding and filtering between them, adversarial networks, reinforcement learning, and local training, all in this one platform. And it's using that digital twin together with an IoT layer to fuse all of that data into the digital twin that gives us a single view of the world. That's done through what we call semantic lowering, this notion of you have a high level ontology. It knows like a pump wants to get 100 gallons a minute at say, 50 degrees Celsius. And that's what you want, right? You don't want BACnet address turn on. What you want is this outcome, and then you back propagate it to how you say it in any given language, whether that's BACnet or whether that's analog. We support the notion of generative reinforcement learning. We actually have some really interesting experiments with this that then we're working with PNNL on extending those. We've done things like, our forward simulation engine then trains a reverse simulation that can then reverse the state back to a time in the past to set up state to then forward back to, so you can pre-set up your state in a more timely manner, as an example of generative reinforcement learning. So when you chain all these modes of learning together, basically you have a supervised learning component of those subgraphs where you're in a supervised environment, being able to train, let's say, a pump or a valve or a boiler. Then you can compose those individuals into these macrographs with that emergent instinct. Then we use model-based reinforcement learning to continue to learn on how that system behaves. And then a model-free gradient action on how do we find our paths. And then this generative portion that really allows the key values that we see there is it allows us to generate lower order models that can then seed the higher order models. So they generatively get trained off the higher order models. They then are used to seed those same higher order models. Some of the things that we see in our pilots, I'm going to focus more on a couple of the other details, but we're seeing on average across a cluster of pilots, 30% energy savings. in just better control and optimization of the existing resources. So that's what we're doing within the framework of the system. What I want to give you a little bit of a sense on the Swift language, like why are we using Swift? How come we went so deep as to talk about the compilers, and what's that all about? So we have this kind of thesis, what if you don't win the framework lottery? What if tensors just don't suit your problem? And what we really feel strongly about is, the emergence of the libraries that we're using today, whether it's TensorFlow or PyTorch, they solved a really hard problem that we really need solved, but then they kind of became our jailer with a point of view. And what if we could kind of release ourselves from the whole AI world, kind of like on their hands and knees below one, parking light in the midst of an otherwise dark, parking lot, that there's all these other places to be explored. And we're a big believer that those places to be explored can be unlocked by generalized differentiability. So we picked Swift for several reasons. This is industrial grade. We needed a compiled system level performance language. We needed something that had a strong type system to be able to enable our type system in quantum. We need high level abstractions, just like Python. And we needed this ability for first-class differentiability. And Swift is the only language with a first-class compiler-supported differentiability system. That was started 4 or 5 years ago by Richard Way and Chris Latner at Google Brain. And today, PassiveLogic is the biggest contributor to this feature within Swift language. And as of the spring, it's usable for production. This is mainlined right into the Swift nightlies. You can download it yourself and use it. And the key thing that we see is when we talk to Apple, we talk to Google, we talk to NVIDIA, what we find is that they're all seeing low adoption of these frameworks, that they're spending billions of dollars, especially at the edge. And so what is the problem? Well, one big problem is that no matter how much your team is AI centric, it's still going to be like 10% of your code, right? 90% of your code is still going to be application systems code. And you're going to have a team for that. You're going to have a big team for that. And then you're going to have another team for your deep learning. And then you're going to have a third team to glue it all together. And it's a lot of work. And so we're just not getting as much headway as we'd like. So what if we could eliminate this gap? So with differential Swift, what we see as an industrial grade compiler-driven environment, we can unify AI and application code. We can eliminate the difference between training and inferencing and enable these typed heterogeneous graphs. And most importantly, it's really, really fast. So this is, as of a month ago, some of the speed improvements that Brad and our team and his guys have made. We're about 190 times faster than TensorFlow at doing these kind of physics problems, and about 120 times faster than PyTorch. Keep in mind that we're still not fully optimized. We've been working on correctness, not optimization. So we actually expect this to get 2 to 3 orders of magnitude faster in the next year. And the thing, if you're using Python, the first thing to notice is they don't actually look that different. In fact, the Swift doesn't have these sort of weird, unnecessary tensor side effects that we had to deal with in TensorFlow. And otherwise, they're at the same level of abstraction. So this could be really interesting for some of you. This is open source, it's usable today. The other tools that we're going to be open sourcing is our introspection tools. And it looks at this notion of fusing systems language together with their AI problems into one. So it starts with this notion that really all your code is graphable, whether you're using native graphs, something like Quantum that is a graph, or object models, classes, they're just graphs. And arrays and tensors, you can conform them to a graph with one line of code. And if everything's graphable, then everything's introspectable. And here's the introspection interfaces that you can just say, well, for my building, find my exterior wall surfaces where certain things are true. And now I have my exterior wall surfaces. And if everything's introspectable, everything's inferenceable. So here's the self-inference of a complex query into your data model. And if everything's inferenceable, then everything's just solvable. And so here's an example in the building space where I'm saying, I want to create a lens. This is a functional notion, a lens where I'm inferencing, I'm introspecting to where all exterior walls are face south, and another lens where all exterior walls face east. And then I want to add a constraint where I say that the relationship between east and south is perpendicular. Now solve for this constraint. So this took 4 lines of code, and I didn't have to leave my domain to solve things using gradients. So quickly, to make all this real, let me just give you what this connected workflow looks like in the real world with Boiler Bob and HVAC Harry using this stuff. So we have a tool called Autonomy Studio that you draw what your building looks like, or import BEM, or bring in scans, and you drag and drop sensors, and you're building up a digital twin of the building and the spatial model. We have another tool called AR Studio that allows you to scan a building, and you can scan about 10,000 square meters or 100,000 square feet of building a day right into a 3D model and with sensor locations along the way. You drag and drop and draw what your systems look like. These are all digital twins again. It looks like a simple Visio drawing, but what the user is actually doing is they're constructing that deep physics graph. It generally designs its own control system from that knowledge. It does the automated point mapping that you can interactively work with and get real-time feedback. And because it understands underlying physics, it can automate our commissioning and tell us where the commissioning problems are, where the building doesn't match the drawing. So this really changes the workflow, simplifies it a great deal, gets rid of programming, democratizes it, but builds us up the digital twin that allows us to then get this sort of automatic analysis, commissioning, building management, and then run it right on these control platforms that are built to just digest digital twins and do the control. This is the little peering into some of the other things we have going at PassiveLogic beyond the autonomous control platform and Autonomy Studio tools that allow you to work with digital twins across the different marketplaces, whether you're a manufacturer of equipment, or you're doing energy engineering and generative design, or you're just an occupant in a building. So I appreciate you guys going on that long journey with me. Thanks.
Thank you, Troy. This was beautiful. I'm sure there is applause in the room, and you may be able to hear it, and there is virtual applause everywhere. So thank you so much. This was very visionary with a lot of topics, and exciting to hear how some of the research is translated into reality. We have time for a few questions. Keep in mind, if you have a lot, Troy will be back later for the panel. So we'll have lots of time for questions, but we can have 1 or 2 now. If you don't want to let him go.
You have a question, you can come into slide to the front. Sorry.
Gregor, did you raise your hand? Sorry, go ahead.
Okay. Yes, my phone, my microphone is on. Troy, I'm wondering, in conventional building operation, we had sequences of operations that somehow needed to communicate the intent of the building operation to a control system. And then you spoke about the entropy generated, or the telephone game, right? In actually generating a building. We do have buildings, a few, the 3% in count, that do have building automation systems seem to work. How do you, I have a new building, and let's say it is not tiny, but how do you convey intent if it's not through written sequences of operation? I mean, how do you start a new construction and you have an overarching energy management strategy that you'd like to work with that involves schedules, and it works events, event-driven control? It needs to be generated somehow, doesn't it?
Yeah, so it's a little bit different mindset of what intent is. So we tend to think that, the sort of fundamental intent is these things that we, what do we want out of buildings? What do we want out of comfort? What do we want out of our systems and energy efficiency and so forth? And I think we have this series of of things that we've done in the past to accommodate the limitedness of our control environment, that we've had to be like, well, I'm going to create schedules and I'm going to do, because you're assuming that the system doesn't have any knowledge. And what I think is interesting is when we meet with, even though it's a paradigm switch, when we meet with installers, when we meet with controls contractors, when we meet with engineers, after getting them around that first hour of the presentation in a different shape than what you guys saw, they're like, wow, I mean, this seems like how it should have always worked. Like I went to school, got a mechanical engineering degree. I understand thermodynamics. What I don't understand is control sequences. Boy, now I can describe things in thermodynamics. That makes sense to me. That would be the engineer's response. A controls guy's response would be in a different light, but around like some of all the pain points that they experience in the realities of making buildings go. And so, yeah, you're right. There's buildings that seem to mostly kind of work-ish, but having done a lot of energy simulation and energy analysis, and then we saw in the lead building market across the gamut is they never work to the degree that they should. And that's, and I didn't go down the rabbit hole, but if you look at the state problem, what you can say is it's an intractable problem to try to program in manual sequences this very complex dynamic environment. And we're just kind of fooling ourselves that we can actually do it. And we mostly kind of pull it off some of the time, but it doesn't work that great. And it only gets to a few of the buildings.
So let me just ask one more time. Does the operational intent emerge in your system, or do you impose it?
So the way that the sequence of operation is really resolved is you really start from something like, in most commercial buildings, comfort, and you back propagate from all the people's comfort needs. You back propagate up to what are all the heating and cooling and ventilation paths that you need simultaneously for all the zones in the building. Now you have the sort of operational requirements of this is what I'm trying to accomplish. And then you take those paths, there's no set points or they're paths. And then those paths are the outcome of your plant. And now again, you have the outputs and you have to back propagate up to what are the inputs? How do I control for that? Along that way, there could be multiple constraints that you're saying that you want to achieve. But in most cases, the basic one is, first, I must meet comfort. And second, how is the most energy efficient way I can meet comfort?
Excellent. Okay. Well, thank you. Thank you. This is absolutely fascinating.
Thank you. Thank you, Troy. Thank you, Gregor. This is hopefully a blink into the discussion that we may have later. So that's wonderful start. I think it's time for a break now. Just to take a 5-minute break.
There is one hand raise, I think, Philip. So do you think we can take one more question? Just quick question.
Okay, make it quick.
Okay, thank you. Quick question. You make it seem like everything is solved already. So can we stop doing research, or are there still a lot of open fields? And I'm thinking, for instance, about integer programming and these kind of things. Is that solved as well?
There's sort of infinite things to go solve, right? And so I think what we're interested in first and foremost is getting better operating systems that are less effort, right? That doesn't mean that it's like the most optimal way you could do it, because optimality is actually probably number 3 or 4 on the list. Number 1 is, can we get building automation into buildings in the first place, right? And so there's lots of really cool, connected optimization and continued work to be done here. But we've taken an ambitious approach to like booting up teams working on all these things in parallel to have a fully built platform around the concepts.
But I have to ask one more question. So how do you get I have to. How do you tackle these other 97% of the buildings that have thus far resisted any kind of smart control? I mean, the strip malls, the light commercial. How do you break that cost barrier?
Well, so yeah, I mean, we have a fundamental belief that Tim Cook doesn't get a better iPhone than you do, right? So there's this artificial segmentation of the market that's been maintained by the existing players, and that's certainly been like business model induced. So we've designed our model and our platform to like have a $2,000 entry point and scales up to those $20 million projects, and we don't like separate out the technology that you get something worse. And so that's the key thing. It's not that they don't want it. In fact, there's often more value at the small to mid-size. It's usually that you don't have the expertise and you just don't have the budgets. And so if you can break the expertise budget, the expertise and the budget barrier, then that's the only thing limiting scale.
Yeah, sounds convincing. Good, thank you for that.
Okay, thank you again, Troy, Gregor, and Philip, also to kicking off our discussion. So let's close the keynote here, take a 2-3 minute break, and try to start the technical session at 5 minutes past, so we can stick with the time. And while the break, hopefully the speakers can check technology. I think the first one is online, so make sure we can share screen. And then take it from there. And I'll see you 5 minutes past the hour, wherever you are. All righty.
Just testing my audio. Can everyone hear me?
I can hear you online, yes.
All right, thank you.
Can the room hear Sharad? Okay, hopefully it works. We'll wait for Matthias to come back because he will introduce you.
Okay. I think you sent me your email yesterday, right? Okay, I think I have it. The slides, right? On the file, right? This one. Yeah. So you can present you using your. Yep. Yeah. I'll just turn it around. You can see.
Can I just give you
USB? Sure.
to see if it works?
Sure. Okay.
This one. Okay, I'm gonna go. Hold on. Thank you. Sure.
Matthias, I think we can get started whenever you're ready.
Okay, sure. Okay, so hi everyone. I'm going to chair the first session. Our first paper is Behavioral Cloning RL Agents for Demand for DEM by Sharath from Kumar. I believe you're online, Sharath.
Yes, I am.
Okay, great. So yep, take it away.
All right, thank you. Thank you for the introduction. So just to give you a quick background about myself, my name is Sharath, and I am a PhD student with the CNRS in France. So my program is organized jointly in France and in Singapore through the University of Grenoble apps and through NTU. And what I'll be presenting today is a bit of work that we did over the past maybe couple of months, which I hope you might find interesting and which leads to a productive discussion. So first of all, also thank you for giving me this opportunity to present the work. I consider it a great honor. So I hope you can see my slides, right?
Yes.
All right. So so to get started, I just go through the motivation for the work that I'm about to present. And you might recognize this image from the CityLearn GitHub. So essentially, the idea is that in the case of district energy management, we have a situation where there are multiple complex agents to control with interdependence between their actions. So in this sort of situation, the point of this workshop is that we understand that there is promise in using deep reinforcement learning as a solution. But as we all know, deep reinforcement learning is somewhat of a nascent field still, as in taking it to production is still quite difficult, and except for a few special applications, it's still not as approachable as other forms of AI, so to speak. And some of the reasons for this would be sample inefficiency. That means that you need a lot of data to train your models. Then there is a certain art involved in shaping your reward function to give you desirable behaviors, for example. And sometimes it's just very frustrating. So you might get a very nice reinforcement learning setup going on, but it just takes a lot of time to learn very simple strategies, such as, I can use solar energy to charge my batteries, that sort of thing. And the idea is that in this particular kind of problem, we have existing ways of controlling buildings, which is through heuristic methods. And what we want to explore is whether we can use such prior knowledge, which is embedded into these heuristic methods, in order to embed them into the reinforcement learning setup, and then from that point, improve their performance. So that's the whole idea with behavior cloning, and then using some kind of RL algorithms for further improvement. So this is the idea behind the approach that I'm about to present. And just to clarify, the problem is multi-building energy management. So there's a cluster of buildings and each one has a certain amount of solar energy available, and each one has its own electrical storage system. And that's what we are trying to control. So just to give a bit more background, there are a couple of papers that I would like to specifically mention, which motivated this whole idea. One is from the team at UT Austin, where it was mentioned that even the RBCs that or rule-based controllers in this kind of environment, they are able to achieve pretty good performance. Perhaps it is due to a specific aspects of the problem, for example, but sometimes it's quite difficult to conclude that we even need reinforcement learning or deep RL based approaches or any kind of complex solutions for this problem. So by manually tweaking or with a slightly complex rule-based controller, we can still achieve very good performance in this class of problems, which is discussed in this paper on the left-hand side on top. And then there are a few other papers where the idea of transfer learning within the context of reinforcement learning are discussed, and to some moderate success, such techniques do work. And this is what we wanted to explore within the context of CityLearn. So to nail it down, the objectives that we wanted to achieve are, first of all, we wanted to encode heuristic behaviors, which are represented by rule-based controllers, into a deep reinforcement learning actor. And then from that point, once the RL is able to imitate this underlying rule-based controller, we want to improve it using data. So that's the whole idea. So for those of you who are not familiar with CityLearn, it is a simulation framework that was developed by the team at the University of Texas at Austin, and we have used it for our research as well. And it allows you to simulate the problem of district energy management, as in it gives you a framework in which you can try out different reinforcement learning approaches to solve this problem, this control problem, where you have a cluster of buildings and each building has a set of sensors. So you get data per building, such as, the load demand, the solar availability, the storage SOC, that sort of thing. And you also get global observations as well about the environment, such as the time of day, the solar radiance, electricity pricing, that kind of data. And the challenge is that your controller, which can be built through any method, MPC, reinforcement learning, rule-based, anything. And the challenge is that your controller should be able to make good decisions about the energy storage systems for each building. And it's at a per building resolution. So if you have 5 buildings in your district, there are 5 control actions that you need to take. So for the purposes of this study, we have a centralized agent architecture. That means that there's one agent which can take in the observations for the entire district and has to take 5 actions, 1 for each building. And the algorithm that we use for the deep reinforcement learning part of it is PPO, which is pretty well studied, and it is based on an actor-critic paradigm. So like I mentioned, the actions here are just to control the electrical storage for each building. So how much to charge or discharge the electrical storage at each time step per building. Now, one important point is that the basis for this idea is to not have to resort to going to a very complicated reward function in order to get desirable characteristics out of your control agent. So we stuck with the simple, kind of simple rule for the reward function, which is just a negative rectified electricity price, or it's the square of this. And that is the only reward that the agent gets during its training cycle. So I hope the deep reinforcement learning formulation of the problem and what we are trying to solve is clear. So this is a slide where I'll
just a question, just a quick question.
Yes,
on the previous slide, why squared?
It's empirical, to be honest. So you sort of want to penalize cases where your agent takes a decision that really inflates the price, but you don't want to penalize it too much that it's really scared to take any actions. So it's a sort of a trade-off. If you give a linear reward, sometimes it gets more aggressive in its actions. So I would say in a single word, the answer is that it's an empirically known to work kind of reward function.
Mm-hmm. But isn't it disconnected from the actual real world concern of a community operator?
Would you elaborate?
I mean, it's aren't we? You mean net electricity cost, or do you mean price? Price or cost?
Price. So this is just the consumption times the electricity price at that point of time.
So it's cost, not price. Okay, now I understand. But I'm as price is per unit, right? So it's like dollars per kilowatt hour would be a price. So yeah, I
at the end of the presentation. So,
absolutely. No, I just wanted to understand y squared.
sure.
Yeah, so like I mentioned, it's empirically known to work, and we didn't want to spend too much time tuning the reward function. So that's one of the reasons why we chose this. And like you rightly mentioned, it's the cost and not the price. All right, so the training process, this is where I would like to spend most of the time for this presentation. The approach that we have is that for the district, which has 5 buildings, each with its own solar and battery storage system, we start by defining a rule-based controller, which is kind of simplistic in its actions. So what it tries to do is that it tries to charge the batteries during periods of low demand, or that when we say periods of low demand, it's not obtained through any data-driven approach. It's just that a human operator who knows that these are the hours of the day in which we have low demand, and therefore I can take these actions. So we have a rule-based actor which does perform quite well in the scenario. And what we want to do is we want to embed the behaviors of this rule-based actor into an actor-critic reinforcement learning framework, but we want it to be trainable. So the idea is that the deep reinforcement learning agent is an actor-critic network. So there are 2 separate neural networks which take separate, or which give you separate, so the actor network, for example, it tells the action to be taken with the batteries, while the critic network, it works, it depends on the algorithm. So it sort of evaluates how good the action taken by the actor is, which is needed for the learning process. So in our approach to get the behavioral cloning aspect of it to work, what was done was that, first of all, the actor network was trained as a supervised learning problem, where we know the states and we know the actions that the rule-based controller would have taken given these states. And all the actor network learns to do is simply predict the actions given the states. So that part is a completely supervised learning problem. And once that is done, we load these weights and then perform a further reinforcement learning step on top of it, which is based on the PPO algorithm. And the idea is that by carefully controlling the hyperparameters so that subsequent updates are not too far away from the underlying actor weights, you can come up with a functional actor and a critic, which then can be used in the future as more data is available to automatically learn and adapt to and improve itself without any further human intervention. So the idea is that we start with a working functional rule-based controller. We embed this knowledge into a deep reinforcement learning framework, and then we use the deep reinforcement learning algorithm itself to get continuous improvement on top of it. So that's the idea in a nutshell. And here are some observations and results that we got from this. So the training was performed. So we have 1 year of data, and the training was performed using the first 10 months, and we use the last 2 months of data for testing. And as you can see, there is a visible trend here where by using this approach of a first cloning step followed by a reinforcement learning step, we are able to achieve slightly higher or slightly better energy costs than what was otherwise possible. And if you look into the actual actions that are taken by this final agent, they still broadly follow the trends that are embedded in the rule-based system. That is, it still tries to charge and charge the batteries during periods of low price or high solar availability, and discharge during periods of high demand. But it learns to make small changes in the magnitude of those actions, which allows it to get better energy consumption numbers, which is shown in the bottom, which means that there's a tighter distribution of the resulting energy consumption as a result of this approach. And so we did compare this approach within the same problem. What happens if you use only PPO and no behavioral cloning at all? And then that agent also gives you some kind of savings, but the actions taken by the agent are a lot less reasonable, so to speak. So it's a purely random exploration, and you might have to try quite a few different hyperparameters before you converge on something optimal. So here you're left with the PPO actor-critic set of weights, which are able to encode whatever knowledge was present in the underlying rule-based controller. And then from this point onwards, as more data is available, you can just use the same algorithm and have it adapt to changes in the consumption patterns, for example. So this is the work that we did, and something that we observed is that the initial choice of rule-based controller, it's very sensitive to this choice. So as you can see, the improvement that we could achieve over the rule-based controller is somewhat marginal. It's not that high. And therefore, this is a result of the choice of hyperparameters, which constrains the algorithm from straying too far away in its action choices. So in a way, we can say that we trade off the exploration aspect of the reinforcement learning algorithm in order to try and get a more stable and working system to start with. So yeah, I guess we are within time. So this is what I wanted to present, and now I'd be happy to take any questions that you have.
Thank you, Shah. We have time for one question, quick one. No, I think we're good. All right, then we have our next speaker, Shotaro Nonoka. That's going to be in person. So let me set that up. This one, right? And then here, share screen. Yeah, but we can turn this so you can put it here, and you can see us. Okay. No worries. Can you guys see our screen or no?
Part of it, it seems.
Uh-oh. Okay.
Now the screen stopped.
Hold on. Or no. No. Okay. Maybe now.
It's almost there, not quite yet.
Oh no. It was working just now. Yeah, but like,
Yeah, I think it is coming.
Yeah.
Yeah, it came.
It's online now.
oh,
Nope.
I had to unplug it actually.
Okay.
Let's see. Sure. Yeah, maybe that'll be better. You're right. So share entire desktop too. All right, now.
Perfect.
Yes.
Great. Now let's go back to this screen. There we go. Please take it away.
I start now. I'm Shotaro Nonaka, master student of Osaka University. Today, I'd like to talk about deep reinforcement learning-based SOH-aware battery management for DR aggregation. In recent years, the introduction of renewable energy has been progressing. However, such output cannot be controlled. So we need more flexibility for balancing supply and demand. With this requirement, DR are introduced in prosumers. DR is distributed energy resource, including PV, battery, HVAC, EV, and the other appliances is placed on the behind the meter, which helps improving demand side flexibility. Moreover, resource aggregator is also introduced in power system. Resource aggregator concentrates various layers to extract demand side flexibility. Examples of flexibility services by resource aggregator include ancillary services and energy arbitrage. Several studies have been conducted in DR aggregation, such as AV, HVAC, battery aggregation. In this research, we believe battery especially takes an important role for the energy management. But the research considering the battery degradation is not exist. So we propose degradation or battery aggregation based on deep reinforcement learning. This is our system overview. Our system consists of balancing market, resource aggregator, and prosumers. Balancing market tolerates the flexibility to balance power system. Resource aggregator concentrates prosumers flexibility and provides aggregated flexibility for balancing market. Prosumers have DR and extract flexibility. In this research, we focus on resource aggregator to control battery degradation of prosumers. Next slide, I explain how to extract flexibility. In order to extract flexibility, first, the balancing market sends the requirement to resource aggregator. Second, the resource aggregator sends order to all prosumers. Third, prosumers respond to the order by changing the battery charge or discharge. Finally, resource aggregator aggregates the change amount of net load and extract flexibility. Then the battery degradation of each prosumers are affected by its own utilization and the resource aggregator's order. So the resource aggregator has to consider both the aggregation and the battery degradation. Next slide, prosumer model in detail is explained. The prosumer model consists of demand, PV power, controller, and battery and grid. Various elements are connected to the controller. PV generation and demand are given. Battery charge and purchase energy are bidirectional. So the negative value of battery charge and purchase energy represents the battery discharge and selling energy. Next slide, how the controller decided battery charge and purchase energy is explained. For given demand and PV generation, the controller calculates battery charge by rule-based. For example, if PV generation is more than demand, prosumers charge their battery. Moreover, if the battery is fully charged, the surplus PV generation is stored to the grid. See the paper for more details about the rule. After controller calculates battery charge, purchase energy is decided to keep the following relation. This is the basic prosumer's behavior before receiving order from resource aggregator. Next slide, when prosumer receives the order is explained. After receiving order from the resource aggregator, prosumer extract flexibility by changing their only battery charge amount. In other words, battery charge is updated to respond for order. Order is required ratio over max charge or discharge, and order takes value in the range of plus or minus 1. For example, if order equal 1, prosumer is required ratio over max required to increase purchase energy by additional full battery charge. If OIT equal minus 0.5, prosumer is required to reduce purchase energy by additional half battery discharge. In this research, extraction is part in case battery charge cannot be updated for given order. To control the prosumer's battery degradation, we introduce battery degradation model. We use degradation model for battery is based on Milner's paper. This represents degradation as a value of SOH. It defines degradation based on the reduction in maximum battery capacity. The ratio of the degradation represented by SOH is like this. Milner estimated battery degradation SOH with the following degradation model. The degradation model includes various physical parameters. On the other hand, from an operation viewpoint, we still have potential of SOH average to control the battery degradation. So this paper's idea is battery degradation control by considering SOH average. We formulate the problem as a Markov decision process to solve it with a deep reinforcement learning algorithm. Proposed framework as shown in the right figure. Environment is prosumers and balancing market. Agent is resource aggregator. State consists of prosumers as SOH level at time t, the required type of flexibility, the required amount of flexibility, and time index. Action is resource aggregates order to prosumer ice at time t. We define reward function as this equation. The equation have two reward terms, aggregation performance and battery degradation. We maximize this reward function. Next slide, reward function in detail is explained. The objectives of this problem are to extract the required flexibility and minimize the battery degradation. Thus, we need two reward terms, RCreate and RDEC. RCreate is deviation between required flexibility and actual aggregated one. RCreate represents this equation. RDEC is battery degradation factor derived from Milner's model. RDEC represents this equation. Battery degradation is affected by battery usage pattern. As explained in the battery degradation model section, we try to control battery degradation by considering SOH average. Therefore, our take for the battery degradation control includes the part of the degradation model affected by SOH average. In the case study, purpose is evaluating the reward term RT for degradation control. We conducted an experiment with the following settings. We can tell for the result, which introduced degradation control term in reward function, the battery life has significantly increased. In this research, end of life of the battery is assumed to be SOH drops below 0.8. as shown in this table, also the aggregation result worsened. The battery lifetime basically improved. For example, the success rate fell by 5.4%, and MAPE increased 5.1%. However, the average lifetime improved by 11.2%, especially the minimum lifetime, which drastically improved by 2.6 times. Conclusion and future work are follows. That's all. Thank you for listening.
Thank you. Do you have any questions online? Oh, let me see. It's here.
Not yet.
No, now we can see. Oh,
No questions yet online.
okay, that's all right. Well, can we find the speaker once again? All right, and I think our last speaker of the session is virtual. Let me go back to Zoom. Okay, so if I'm not mistaken, gonna need to read the names. The last session, last paper of the session will be by oops, cannot load the conference program. Okay, so the last paper will be by Kuldeep, our TPC member. Deep reinforcement learning with online data augmentation to improve sample efficiency for intelligent HVAC control. All right, Kuldeep, thank you so much.
Thanks, Matthias. So let me share my screen and you tell me if it is visible.
Sure.
Yeah. Are you? Yeah. Okay. Okay.
You can see.
Nice. Okay. So hello all. I'm Kuldeep Purte. I am research scientist in computational urban sciences group at Oak Ridge National Laboratory. So the topic of today's presentation is deep reinforcement learning with online data augmentation to improve sample efficiency of intelligent HVAC control. So first of all, let me acknowledge my contributors and co-authors, Kadir, Jeffrey, and Helia. So myself, Kadir, and Helia are from ORNL, and Jeffrey recently joined National Renewable Energy Laboratory. I would like to remind you few comments that Sharath has pointed out. So I mean, we know that deep reinforcement learning has started showing a very good success in real-world application, complex real-world application, specifically control application, such as building energy optimization, and we are seeing many of the applications throughout this workshop presentations. Most of the time, it happens that we tend to train our RL agent in simulated environment. For example, CityLearn and some Energy Plus kind of environment. And that type of training is called as offline training. So you first train your model or the RL agent in simulated environment, and then you take that pre-trained model. Then if you want to deploy in a real environment, you deploy it. So that's the most of the current trend looks like. As Sharath also correctly pointed out, that this deep reinforcement learning based control sometimes face challenges when it comes to actual real world application or deployment. So one challenge is related to sample efficiency challenges. So these are data driven methods, and to basically obtain a representative policy, efficient policy, the reinforcement learning agent needs to do a lot of interaction with the environment, collect the data, and it takes time. And depending on the application and the complexity, that time varies. So sometimes it is not possible to allow RL agent to explore in the real world environment. And that's why we basically first train your agent in the simulated environment. And also there are some challenges related to comfort and safety. So for example, during the training process, initially RL agent tends to explore more. So if it is HVAC control problem and RL's action spaces to set points, so RL will try different set points and try to explore the environment, how it is reacting. Maybe a homeowner will not be very happy with the random adjustment of the set point. So those are the practical challenges. And in this work, we try to address the sample efficiency challenge. So what I mean by that is we want to reduce the initial training period or the exploration period of the reinforcement learning agent through data augmentation approach. So in this work, we came up with a framework called Reinforcement Learning with Online Data Augmentation, RLDA. So in a nutshell, we used time series based time series data generator, which is called as a time GAN. So it is a generator that we have used, which will essentially take time series as input, and once it is trained, it can produce similar representative time series. So that is our data augmentation module, which we use to address these sample efficiency challenges. And we evaluated the approach, and the experimental evidence proposed that this particular framework and the approach will definitely improve the sample efficiency. But there are a few limitations that I will highlight towards the end of the presentation. So let's see how this RL framework looks like. I would like to summarize this entire framework. So on the right side, this is typical reinforcement learning setup, specifically in the context of, say, deep reinforcement learning, where you have your RL agent, and then you have a replay buffer memory. So if you recall, this replay buffer memory basically stores state, action, reward, and the next state tuples in a sequence. Okay, and throughout the training, our RL agent will basically extract some of the tuples at random, and then it will perform some training. So that is the general deep Q network kind of training scenario. So now what we are trying to do is, so this is the data that RL agent has collected over some of the interaction. So let's say after day 10, whatever data that it has collected, we will use that data and we will invoke data augmenter. So now when you consider these tuples, state, action, reward, and next state, and when you consider a series of those tuples, we can consider them as a time series of tuples. Okay, and once you have that time series of tuples, you can use those tuples to train your data augmenter. And since those tuples have some temporal correlations, we went for a time series based data generator, which is time GAN in this context. So time GAN is basically trained, is basically invoked at, say, particular time during the RL training. Say, for example, after day 10, you then train your GAN network, time GAN network, with whatever data you have, and then after training, you use the generator to generate the similar trajectories or the sequences of your tuples. Now you have the actual data, real data, which is collected by your agent with the interaction, through the interaction with the environment, and then you have some generated data or the synthetic data that we can call. So what you can do, you will combine these trajectories or the time series of these tuples along with your data, actual data, and then you use them in combination with in combination with each other for RL training. So that is the entire training loop. So we included a module for the data augmentation. For experimental setup, so we wanted to evaluate the performance. So we used data for summer and specifically for July and August month from a typical meteorological year for the location of Knoxville, and we trained this model for cooling mode. And we in our past work we developed we have our in-house simulation model for this particular two-story building. It's located in Knoxville, Tennessee. And we use that for training. Now, considering the deep Q network setup, so these are the state space, and we try to keep it a little bit simpler in this case. So state space include time of the day information, indoor temperature for both the zones, time of use price signal, electricity price signal, and outdoor temperatures. In action space, we have two set points, basically 70°F and 74°F. So these are the discrete set points that we have used within the comfort range. And the reward function is the negative of total energy cost. So it is slightly simpler formulation as compared to our prior work. Yeah. And then since we wanted to emulate a real world setting where you don't have an opportunity to basically train your model for multiple episodes, to emulate that setting, what we put few constraints. For example, DQN is carried out only for one episode. So it will emulate that. We have installed installed your DQN agent from scratch into the environment, and now it will just keep on learning, and there is no opportunity to go back and then perform multiple episodes. So that is to mimic that behavior. And to accommodate the random behavior, we carried out this training for 50 iterations, and then we collected daily cost of RL's action, and then we after to compare the performance, we basically then average out the cumulative daily cost for these 50 independent repetitions. For this particular experiment, we tried with data augmentation on the day 10th, and this number was chosen again empirically. We tried with day 5, we tried with day 15, and then we found that for day 10, it performed well. But again, that is one of the things that I will mention into the limitation part. This is the DQN training setup that we have. Most of the parameters are very much similar to our earlier work. For example, control step would be 15 minutes and some learning rate and optimizer. The specific thing which are the specific parameter of the time GAN are related to sequence length. So sequence length is 16, and then training iteration for time GAN was 10,000, set to 10,000. So here I would like to highlight that the meaning of sequence length is, so basically to train time GAN, you will first take the entire time series of your tuple, you chop them into the sequence length of 16, and then you collect your data, and then you form your training data. So that's the meaning of the sequence length. You can train time GAN or the similar time series generator with different sequence length also. And through some trial and error, we found that 16 is a decent sequence length. Then coming towards the evaluation criteria. So basically we used a fixed set point baseline of 74°F. And we ran a reinforcement learning without any data augmentation and reinforcement learning with data augmentation for 62 days of summer months, July and August for the Knoxville region. And then we repeated this training for 50 times to collect the average of cumulative energy cost for these 50 iterations. We then compared when conventional RL without data augmentation has crossed the baseline versus RLDA's energy cost has crossed the baseline. So that was our evaluation criteria to understand whether it has learned faster and in other terms, whether it has improved the sample efficiency. So these are the results. So you can see that in the green dashed line represents the baseline cost, cumulative cost. Sorry, the blue one is the baseline cumulative cost. The green is the reinforcement learning with data augmentation, and the red one is the reinforcement learning from scratch without any data augmentation. So you can, at first instance, you can observe that there are those graphs are very close, but when you zoom into this particular section, you can see that reinforcement learning with data augmentation crossed the baseline cost on day 28, whereas reinforcement learning without any data augmentation crossed the baseline energy cost on day 39. So this gave us experimental evidence that the data augmentation is definitely going to help reinforcement learning training. So you can see that RLDA basically learned almost 11 days earlier, similar behavior 11 days earlier than the RL without any data augmentation. So which is somewhere around 28% improvement in the sample efficiency or the reduction in the data that it required. So that was our observation. Now coming towards some of the points that I would like to highlight, which could be the future research direction. So the synthetic trajectories or the synthetic tuples that are being generated by TimeGAN may contain some low performing tuples or bad tuples where RL agent might have taken some bad decisions. So there needs to be some filtering mechanism after generation, which will filter the tuples before injecting them into the replay memory along with the actual data. The most important thing that we found was TimeGAN training is computationally expensive. For 10 days worth of data, it took around 1 hour of training, somewhere around 50 minutes of training, 50 minutes to 1 hour. We do feel that we did training on the CPU, but we do feel that if we train that model on GPU, it will definitely accelerate the performance. But at the same time, there are other approaches like time VAE that we can also use, which are computationally less expensive. And also the last point that we used day 10, at least in this work, we chose with some intuition, but I think there has to be some mechanism that will let us know that, okay, this particular day X is now sufficient. Whatever data that you have collected is sufficient. Use that data and now do some data augmentation. So there has to be some semi-automatic or automatic mechanism which will tell us when to invoke the data augmentation. And also this work needs to be evaluated for entire year to accommodate the seasonal variations. So those are the few limitation, rather future directions that I would like to highlight. And with that, I would like to acknowledge our sponsors, which is AI Initiative, which is a part of Laboratory Directed Research and Development Program at Oak Ridge National Lab. With that, I would like to thank you all for your attention, and I'm happy to take any questions.
Thank you, Kuldeep. Are there any questions? Yes. Yeah, maybe you can come a little closer to the mic is there. Okay. Yeah.
Hi, thank you for your presentation. I'm Harvey from Lawrence Berkeley Lab. So I have a question about the method. Looks like you're generating the state action sequences under normal conditions. But what if we have a time use rate? We have a storage and we have different peak hours. Does your method can your method generate those kind of synthetic data?
Yeah, so thank you for the question. So do you mean some kind of extreme conditions, whether this method is able to generate the extreme conditions also?
Yeah, so for example, if we know the peak hour is during afternoon, we want to preheat or pre-cool our building, right? So your set point schedule will be very different from normal schedules.
Right.
Yeah, so
Right.
can you generate those kind of synthetic data?
Right. I think, yeah, that's very interesting question. So let me point out to this particular fact that we allow RL agent to perform its training and the action for some period of time. And during that period of time, if those conditions are being accounted or happened, so that data will be used by this time GAN to generate. So now so based on your question, if those extreme cases are already represented in this data, then time GAN will definitely able to generate some sufficient representative samples into the synthetic data. But at the counterpart, if those kind of conditions are not available in this initial training period, then maybe we need to think about some alternative way to either inject that knowledge to some transfer learning mechanism, or maybe through some rule-based approach. So right now, we haven't thought about those kind of scenario, but yeah.
I see. Yeah, thank you.
Sure. We have time for one more. Hi, this is Shuhan from Harvard. I have a quick question. So I wonder, how did you calculate the percentage improvement of the sampling efficiency? Because visually I saw all the results are similar, but the improvement is 28%.
Yeah, so the improvement here is not in terms of saving energy cost, but improvement was in terms of how much less training time, or rather less training data that it has used. So for example, here reinforcement learning with data augmentation beat the baseline cost on day 28, and the similar performance, average performance was observed for RL without data augmentation on 39th day. So RL with data augmentation was able to achieve similar performance at least 11 days earlier than the RL without data augmentation. Yeah.
Thank you.
And as far as the cost is concerned, I think you can see that the energy cost was slightly reduced as compared to RL. It was not like major difference. But yeah.
Okay. Thank you, Kuldeep. We can thank the speaker once again.
Yeah. Thank you so much, guys.
There was a question on the chat, but maybe we can take that while we wait.
Yeah, let's. There's one more question in the chat. Take that online. I mean, in the chat, please. We're running about 10 minutes past schedule, so let's take a 5-minute break, and then meet again 5 minutes past the hour, and for our second keynote of today.
Yeah, maybe we can come here.
Is that okay?
Sure.
Good. Let's meet 5 minutes past the hour.
Yes, yeah.
Kuldeep, here, there's a question for you. While everyone is on the break, there's a one.
Yeah, hi. Hi, I'm Alice from Harvard. I'm sorry, probably I missed the first part. So, do you mind explain more how did you do the data augmentation to save the training time? How did you do that data augmentation in the first stage?
Yeah. So data augmentation will require some data. Okay, let me go back and share the screen. I think that will be easier. It will be quick also. So this is the training loop, the normal training loop. So what we are doing after some particular training time, we are invoking data augmenter, and this data augmenter can be any time series data generator or augmenter. So we are allowing RL agent to learn for some initial time, say for example for 10 days. And after that, it will use the data that has been collected for these 10 days. And that data is currently the tuples that it is being collected in the replay memory. So we take those tuples in the form of the time series, and then provide those tuples to invoke data augmenter, provide those tuples to time GAN. We train the time GAN. It will we will allow it to generate the synthetic trajectories or the tuples. Use those tuples along with the actual tuples during the training, and then you will continue the training thereafter. So that's the current training process. Of course, I mean, there are various possibilities that we can play around.
So basically, you just like multiply the collected data by a factor. to augment the current new collected data, right?
Yes, exactly. You have a limited data available. So for example, if you are collecting 4 tuples in 1 hour, then at the end of say 10 days, you might have, I think, 960 tuples. So that is very limited data. Now, depending on the quality of the data generator, it will take 960 tuples in the form of time series. It will train, and it will be able to generate a few more representative trajectories of the tuples.
I'm also wondering, how did you define that factor you are going to multiply to those like 16 new data, 96 new data you collected?
I didn't understand. So you want to understand how we are combining those synthetic generated data with the actual data?
Right.
Okay, so right now we are actually combining the generated data along with the actual data that is being generated. We haven't made any distinction that, okay, this is the synthetic data and this is the actual data. So there could be some possibility that we will choose this synthetic data with some probability of 50% and combine that with the actual data with some probability. So we haven't used those approaches. We are actually combining directly without doing any filtering or without any selection criteria.
Okay, I see.
Yeah, this is just the preliminary attempt to understand whether data augmenter can improve the sample efficiency.
Thank you so much. Thank you.
Yeah, thanks.
We're having 10 minutes break, right?
Yeah, 5 minutes. We should be back at 10:05.
Okay, so next session will be
In about 2-3 minutes, yeah.
Yeah.
Keynote.
Okay. Let me come back in 3 minutes.
Matthias, how many people are in the room roughly during the session, not during the break?
There were up to 9.
Cool.
Yeah.
Okay. Yeah, there's about 30 people online, so it's about 40 that registered, so roughly what we expected. That's cool.
Yeah.
Let's wait another minute and then we can get started.
Zoltan, can you see my
Yep.
slide?
We can see your slides, and I
Yes.
think Kuldeep, we can get started.
We can get
Kick us
started.
off. Yes, please.
Okay. So welcome all of you to the second session, and we will begin this session with a very interesting keynote talk. This is talk by Gregor Henze, and the topic of his keynote is opportunities and challenges of building energy management using advanced building controls, which is the very topic or the theme of this workshop. So about Gregor. So Gregor Henze is a professor and holds a CV Shelke chair in Department of Civil, Environmental and Architectural Engineering at University of Colorado. His research emphasizes variety of topics in this particular context, which includes reinforcement learning control of building energy systems, building thermal mass, a refrigeration system, model-based benchmarking, fault detection and diagnosis, control strategies of for mixed mode buildings, uncertainty quantification of occupant behavior, and so on. Sensor fusion algorithm. So there is some flavor of IoT, energy analytics, decision analysis, and so on.
Kuldeep, I think that's good. That's good.
There is some more.
Yeah, I know, but I think let's get started because we have limited time in this workshop.
Sure.
And appreciate your words of welcome. Welcome everyone here to the second part of the day. Would like to express my gratitude for allowing us to be here, and for also my gratitude to the organizing team for setting this up. This RLEM workshop is always an exciting event, and really cuts to the heart of what I really am very passionate about, which is making our building stock just smarter and more responsive to what we want them to do. And so here today, we have a few minutes together, and I'm going to let you know that I'm doing this together with a PhD student of mine, Shurav Day, who's in India right now, and who's also unfortunately suffering from a pretty heavy cold, and Thibaut Matsulo, former postdoc in my group, now at NREL. So the three of us would like to do things a little differently. Rather than just giving you information, we would like to have this be more interactive. And so we will come to breakpoints in which we'd like to actually have your feedback as experts in the field. And I think it's evident that we all share a common passion, and I would like to see if we can somehow have some insights generated from this team today that goes beyond just what I'm talking about today. So clearly the context for advanced building control is not new. We all know that buildings are responsible for significant contributions in primary energy and are the bulk consumer of electricity in the United States, 3/4 of electricity. We spend, as you know, a lot of time indoors. We all know the statistic about something like 90% that we are indoors. And so it really matters to make our buildings smarter. And our HVAC systems, which is the focus today here, is the building energy systems, are major consumers of energy in residential and commercial buildings. So what is the significance of advanced building control, right? Clearly, one hope is that we can optimize multiple objectives in a performance-based approach. Rather than retrospectively seeing how a building did perform, we actually have a measuring stick and can say, I want you to perform to a certain set of criteria of desired performance characteristics. And those clearly are not just thermal comfort, but increasingly have to do with indoor air quality. I mean, we've gone through several years of a pandemic that had a very strong connection to indoor air quality, visual comfort, and carbon emissions, of course, are becoming increasingly important. Now we hear that hospitals, for example, the Vatican is asking the Catholic hospitals in the United States prioritize decarbonization in their hospitals, and the hospitals just don't know how to do that because they are highly constrained in their operations. So we want advanced building controls to really give us improvements in health and productivity for occupants. But we all know as we're decarbonizing, we have a greater share of variable and uncertain renewable generation. We'd like our buildings to provide grid services that have been mentioned several times today. And we'd like to, of course, allow these advanced controls to interact and integrate emerging IoT technologies. And last but not least, there's a potential for personalized controls that allow us as the human to become more productive and allow for a more customized environment than the one-size-fits-all that we're typically given. So all these things are on the horizon and let us wake up in the morning and work on building control, I believe. What we're doing thus far is we have the rule-based controls, the heuristics that we have. Those aren't written down in an afternoon, right? If you see ASHRAE guideline 36, for example, that took many, many years of building professionals to come together and agree on what a high performance sequence of operation would be. And in the context of Troy's presentation, I asked, how are they conveyed these sequences of operation? And in his PassiveLogic ecosystem. But we have those. We clearly have standards to abide by that pertain to thermal comfort and indoor air quality and energy performance. And over the last, I would say 25 years at least of my past, I've worked on model predictive control with its flavors, and reinforcement learning control has more recently, through the stochastic gradient descent revolution, found its way back into the mainstream. It was something that in the late 90s, there was quite a bit of work on learning systems. There's the adaptive house by Michael Moser that goes back to 1992. So the idea of learning systems isn't all that new, but we have new computational capabilities that allow us to do this. Recently, through Florian Dörfler at ETH Zurich, we have data-enabled predictive control emerging, which goes away or does away with some of the downsides of reinforcement learning. Is also a very promising approach. So we have these existing and new approaches that we can choose from, and we clearly see opportunities from all these new approaches. Carbon emission reductions, grid signal response, performance-based operation, right? I mentioned that we can now use measurement sticks and apply them. The ability to consider multiple of these objectives at the same time, and adaptive changes in building operation, not having to go back and reprogram. Truly having a building become a learning building and a better citizen of the electric grid system. Those are opportunities that excite, I think, all of us here in the room. But then we have those challenges, some of which were addressed today. I would call the first one the snowflake issue, right? Every building is unique, and Troy mentioned that already. There's also resistance in our industry to try unproven technologies. There's that risk perception, and there's a certain hesitation to try new things in buildings. We also see the need for deep building engineering expertise to implement some of these advanced controls. And we've also seen, the performance improvements of smart or advanced control aren't often that great, right? There may be just an incremental benefit relative to some of these rule-based controls. We need lots of data to train some of the methods addressed, and in many of the buildings, we just lack the sensing capabilities and the building automation systems. Another challenge is the algorithmic scalability and just the building scalability, security, so that people feel like their systems can't be hacked and the buildings are secure from an IT perspective. So these seem fairly daunting, and just to basically turn this to you, I'm wondering, did we miss anything in terms of challenges and opportunities that we have today in 2022 to implement advanced building controls? And I'd like to open the floor for that for just a couple of minutes. Zoltan, is there anything I do to open the floor?
No, the mic's open for a question or comment. I don't know if Troy's listening in, if he has a comment on did Gregor miss it completely, or did you agree 100%?
No, I think this is a really
50%?
good a good summary, and I love that you didn't hold anything back to coming up with all of the stakeholders here. I mean, there's a really good like diagram. So I think that's a really great lead up to the big question here.
Linda has
Gregor, I have a, oh, go ahead.
Linda has some suggestion, I think.
Yeah, hi, I'm Linda. I'm a PhD student at Erasmus University in Rotterdam. So actually my research is more on electric networks. So what I'm actually wondering, if I listen to all these talks, is that everything is more about buildings in itself. Every building is unique, but there's less talk about how buildings can sort of maybe work together to achieve those goals, for example, in these kind of networks, because I think our grids, like smart grids, become more and more interconnected. So I'm wondering if that's also something you're considering here.
Let me just see, I'm missing something here on my IT side here. Okay, I think I'm back. Linda, so you're saying that buildings are not islands, but they're interconnected to smart grids. Is that what you're saying, Linda?
Yes, indeed. And therefore, I think there is also a connection between buildings because they're connected to the grid. And I think that's something I, like from outside, I'm not really seeing in the talks. And I'm just wondering whether that's something you're also considering.
Yeah, I think we had the first technical talk after Troy discussing kind of an urban district perspective.
Yeah.
And I think clearly that is the direction. I would almost say, Linda, you have a good observation. We've been very focused on making individual buildings smarter because the ownership and stakeholder situation is fairly defined. As soon as you go to an urban district, you have many more stakeholders at the table needing to agree. But it's clearly the challenge, right? As we continue to urbanize, how can we make our cities, our new urban districts, be more sustainable, more efficient with our resources, make better use of the renewables, make better use of the installed systems. I think you're spot on, and I think that's one of the motivations for Zoltan to develop the CityLearn environment to take us to the next horizon, which is clearly an urban perspective.
Thank you.
Is there a question in the room? Yeah, good.
Yes. Hi. Not a question. Mario Burgess here from Carnegie Mellon University. I think in the slides you covered it perhaps, but not pointing your finger directly at it. The issue of understanding human behavior, human intentions, and human preferences, generally speaking. I think that's both an opportunity and a challenge. Buildings are there for the humans, and there's not been a better time to understand sort of the social dynamics than what we have access to now. So I think both of those sides of the equation should be put in there.
Oh, if I may say that you're hitting on a super exciting area of work. I'm just thinking of Andrew Sonta's work at EPFL, who's really focused on this dual role of buildings to serve the environment and to serve people, and to focus on the social network role that buildings serve at the same time that buildings have a huge impact on the environment. So I think that's an absolutely spot on remark, and I think It is a frontier that we as engineers often stay away from, because building behavior is just so complicated and so fickle that maybe it's a lack of comfort, but I think that is an open frontier for us to tackle. I totally agree.
Gregor, I think we can continue. And if you have other comments for Gregor and Troy, keep them and come back to them later when Gregor asks again for input in about 10 minutes, and then later in the panel again. I have a few. I will not ask them now, but I'll ask you later, Gregor, if you're ready.
Perfect. Okay, so with me here this morning is Dr. Thibaut Marzullo. He's going to work with me here. I'm his extended arm on the slide deck, but he's also in Colorado. But at -10 degrees, we both felt like staying huddled in our place. So Thibaut, good morning. I hope you're doing well. So I'm going to allow you to talk about the environment that we've been developing now for the last 3 years, which we call the Advanced Controls Testbed. And just to give it away, it's free and it's an amazing system that we would like you to.
Gregor?
Yep.
I think the slides are shared wrongly. Like we're seeing the presenter slides.
Yeah, you need to swap the display, I think.
Oh, I do.
There's on the top
There's an
left.
option on the top. Yeah.
There you
Did
go.
that work? Is that working?
Yes.
Okay, good. Well, with that, thank you for your patience on the technology here. So Thibaut will describe work that we've been involved in for the last 3 years approximately. And it is an open invitation for all of you here attending this workshop to basically take a look at it and see what it can do for our joint interest in making buildings smarter. So Thibaut, are you there? Can I let you jump in?
I am. Good morning. Can you all hear me?
Very well.
Perfect. So good morning, everyone. And well, thank you for giving us the opportunity to talk at this RLEM webinar. So as Gregor said, I'm here to present the Advanced Controls Testbed, which I'm going to call the ACTB for the rest of the presentation, so as to not confuse everyone. Gregor, would you like to switch slides? So today, usually building energy simulation frameworks, there are quite a few out there. They exist in many flavors. However, they have a few shortcomings. So we have noticed that some are specialized in energy modeling, but they do lack control modeling capabilities. So I'm thinking about frameworks such as Energy Plus or Open Studio, for example. If we're looking on frameworks specialized in controls modeling, they usually rely on highly simplified building models, which is not ideal for developing advanced controllers that are acting on buildings that are rather realistic. If we look at the scale of simulation, well, we can find single building simulation, or as was mentioned before, if we look at large scale simulation for multiple buildings, we usually rely on simplified building models, and we're not always looking at advanced control modeling capabilities. And finally, we can find good performers in all of the above, but often these are custom tailored frameworks. Sometimes they're closed source, and it's not always that easy to extend them to different studies. Next slide, please. So we developed the Advanced Controls Testbed with an idea in mind that if we had an ideal framework, we would be able to offer both highly realistic buildings, but also simplified building models. We would be able to use realistic controller models and interfaces to some well-known advanced control libraries. Yeah, we would also feature streamlined workflows for developing new test cases. And yeah, we would enable large scale simulation, whether it's centralized or distributed. And we would also be able to extend that framework with other models that are not centered around building energy, such as grid models or on-site generation, microgrids, etc. And as Gregor said, very importantly, we would make it free and open source. Yeah, and we would also use widespread and well-supported programming languages and modeling framework for a better user experience. So the ACTB is based around a framework for benchmarking operation performance in buildings, which is called BOPTEST. It's developed as part of IPIPSA Project 1, and it allows researchers, people to benchmark building controllers on standardized test cases. BOPTEST and Alfalfa, which is they work together in BOPTEST service, are two frameworks that allow us to compile and simulate models packaged as functional mockup units or FMUs, and use the JModelica simulation engine, which it gives us access to Modelica for simulation purposes. With the Alfalfa part, we are able to propose decentralized simulation using cloud-based computing capabilities and also local simulation. And we also offer an API for extended simulation management. So this API includes an external clock for stepping simulations, for uploading, initializing, retrieving simulation results, and retrieve key performance indicator calculations. And finally, we have developed a few external controller interfaces that can read and override model variables. So we're talking about sensors and controls within the building model or any additional model you would like to plug into your test case. So earlier I mentioned that we offer both high fidelity models and simplified models. On the high fidelity side, we rely on SPAN of Energy Plus, which we commonly just call SPAN. So SPAN offers a framework for co-simulating both Energy Plus models to simulate envelope and loads in a building, and Modelica models for simulating HVAC and controls. So this gives us the opportunity to really take the best of both worlds, the Energy Plus capabilities for simulating the building itself, and the Modelica capabilities for simulating systems. Yep, another click, please. Thanks. So so that's the high fidelity part. On the simplified model part, we understand that some applications are high performance or cannot afford to simulate a complex model. So we also developed a meta modeling framework, which is able to automatically extract a number of meta models, either from other simulations, such as the SPAN simulation, or from historical building data. As I said, we could use these meta models in high performance applications. So we're thinking about training reinforcement learning agents, or as my colleague Shurav will show in a moment, or maybe as prediction models for MPC. We have based these meta modeling framework on some well-known and mature libraries. So we can offer some linear methods that are based on the scikit-learn library. We can offer regression, random forest regression trees, but we can also extract models using system identification based on the SIPI library.
I had a quick question here in this context, Thibaut. What if someone says, well, all this Energy Plus and Modelic, it seems like awfully complicated. Are there any developments on the horizon that maybe allow to lower the expertise level to generate these detailed models?
So yes, SPAN is extremely new. It's the new kid on the block, and now that we know it's working, there are undergoing efforts to make it more user-friendly, integrated with other frameworks that are not aimed only at researchers who might, not mind diving into the nits and grits of coding and creating a new model and spending considerable time tuning their models, but also to engineers who want a more plug-and-play solution. So things are moving very quickly, and we can expect to have sometimes in the near future some additional ways to create span of energy plus models. So yes, right now our audience will look at these models into a Modelica IDE, and tomorrow you'll be able to probably click up to 3 buttons and end up with a span of energy plus model. So
that's the exciting developments.
Yes. So Jan Dragona is asking if this environment is already open sourced. Yes, it's. I'm going to give a link just a little bit later on in the presentation. You can. I'll get to that in a second. So in terms of interfaces, because I just talked about the backbone that allows us to simulate buildings, we have developed 2 interfaces. So the first one is an interface to the OpenAI Gym library. That's also based on some work done by the PopTest team on interfacing OpenAI Gym. So this audience would most probably know what OpenAI Gym is. It has a lot of support through an extensive user community, many publications to which you probably personally contributed, and test cases. So we have customized an environment and integrated it with both DACTB and the meta modeling framework so that you could develop RL agents that can either interact with what we call the real quote unquote building, the high fidelity building, or a simplified model either for training or other purposes. So that's the first interface. The second one we developed is aimed at model predictive controllers. So that one is based on DoMPC, which is a library that provides a framework for a modular framework for developing MPC, which is based on high performance solvers. And again, we integrated it with the ACTB so that it could leverage the meta modeling framework for using for prediction models and spawn for the real building. So now that we have talked about the architecture itself, I just want to present really quickly 2 test cases. So these test cases are based on the reference small office building from the DOE reference building models. I'm going to talk about 2 MPC test cases, one where we have a target demand limit, and I'm going to talk about it in a second. One where we have some indoor air quality monitoring, and Shurav is going to present some examples with reinforcement learning. So in the first one, we are controlling a 5 heating coil for 5 HVAC systems that are serving 5 thermal zones in the small office building. We have defined a demand response event in which there is a whole building target demand limit of 5 kilowatts between 2 p.m. and 6 p.m. during the day. And we are using a prediction model that's been extracted using the framework, using system identification on some data generated from the real building. So this prediction model is what you can see in dotted lines on the right-hand side plots. So this is what the MPC is predicting. The solid lines is the actual data. So we created a cost function that was based on thermal discomfort, on the cost of electricity, and on the cost of demand limit violations. And finally, there's a cost of control to encourage gradual changes in control input changes. So on the right-hand side at the very top, we can see indoor temperature and set points in the 5 zones. We can see the heating coil command in the second plot. The third plot is the whole building electricity demand in kilowatts, within blue, the target demand limit. And as you can see, the MPC is keeping the temperature mostly within bounds for thermal comfort, and also respecting the demand constraint, the electricity demand constraint. Next slide, please. So on the same test case, really, we removed the target demand constraint, and we replaced it with a constraint that would keep CO2 concentrations indoor below 600 parts per million to increase productivity within the space and to give, well, better air quality. So this time we are not only controlling the heating coil power output in the 5 zones, but also the outside air damper opening fraction. And to predict indoor air temperatures, we're using the same model, the same prediction model as before, but we also added a second model for predicting CO2 concentrations that is based on differential equations. So again, at the very top, we have set points and indoor temperature, and we added the CO2 concentrations. So that's, again, simulated on one day in the small office building. Next slide, please. So yes, Jan's question, the ACTB has been released on GitHub, so you can go ahead, try it, please break it. Spoiler alert, might break. Just post issues. We're active on that GitHub repository. We address issues, and we have quarterly updates on the development branch. Please monitor them. They're pretty exciting. We have multiple building capabilities. We're active on that development branch. We also plan on releasing 2 stable releases every year, and we have some more interesting developments coming in the next release, 0.3. We are also working on a graphical user interface for those of you who are tired of terminal windows and, well, you know the drill. So we have a link for our GitHub page. Next slide, please.
I just want to point out that the link says MODRLC. That is work in the context of a DOE funded project on multi-objective deep reinforcement learning that motivated the development of the ACTB. That's why the link has that acronym in it.
Absolutely. So in conclusion, I hope we have showed that the ACTB offers a practical and well-supported way to use interfaces to its virtual building simulator. And since advanced control methods are the focus of the ACTB, we provided a framework for formulating complex problems that use realistic building models. We use SPAN models because they're more realistic than pure energy plus models for controls applications, but we also consider high performance applications with the meta modeling framework. The test cases are scalable and are not limited to single building applications. Model libraries are expandable, so if you want to go ahead and add models to the Modelica side, you can. If you want to develop more complex energy plus models, you can. If you want to lump many buildings and systems together, you can. And finally, what I want to demonstrate today is that we provide a virtual environment that is much closer to reality than classic building energy models. So that offers us the possibility to develop advanced controllers that are hopefully better prepared for field testing, and we are taking a few extra steps in the direction of real world. So thank you for listening. I'm open to questions you might have.
Any comments? And we have one more intermezzo, right, Gregor, from Shuraf?
Yep. Yeah.
Okay, perfect.
Evolved, this is Kuldeep. I have one quick question. So you shown that there are two modules. One is do MPC, and then there is another which is OpenAI Gym. So suppose, is there any flexibility currently available if you want to develop your own or do some customization in the existing RL algorithms and try to apply that in the context? Is that flexibility available, or do we need to like do some extra things?
So the OpenAI Gym interface is actually a custom environment that links to the ACTB through some API calls for initializing, stepping, retrieving results, and resetting the simulation. So we try to stay as close as possible to the OpenAI Gym framework, and it's really an interface. So we have not modified any functionality. We are not limiting any functionality. So whatever you can do on the OpenAI Gym framework, you can do on the ACTB.
Well, yeah, good. Thank you.
Super. Thibaut, thank you very much. And with that, I'd like to say a hearty welcome to Shurav. I hope you're feeling a little better than you did last night. You were very sick. He's nodding, so I presume he can speak. We were thinking, let me see if I can do the share again. Is that working? Okay, do I have to switch the slide again? Is that correct?
Yes.
Okay, got it. Okay, super. Trying to work with an iPad and a PC at the same time. Okay, so we're coming to the last part on RLC advancements towards building implementation, which is really this workshop's topic. The work that's shown now is reliant on or is utilizing the ACTB that Thibaut just presented, okay? So I think as was mentioned in the introduction, the operational objectives we have for buildings are really changing. What used to be just tenant cost is now moving to kind of a smorgasbord of, I want to reduce carbons. I want my building to be flexible. I want indoor air quality to improve. And of course, I want people to be comfortable and productive. And then, of course, I want to have resilience. So it's a complex melange of objectives that we're trying to manage. And we know that, as was highlighted by Troy as well, is that the existing rule-based controls, they're often suboptimal and they take a lot of effort to be doing well. So there's an engineering expertise that is required that with an aging workforce, we apparently cannot afford anymore. We also know that model predictive control has been shown to be successful, but with an incredible investment of time and engineering effort, and also requires a sufficiently accurate model. And this brings reinforcement learning onto the stage. And we have to ask, well, is pure RL control this solution we're looking for? And we see some positive motivations to pursue RLC, right? Which is, it has the ability to respond to this multi-objective question or a perspective that building owners are increasingly adopting. It learns by interaction. It can learn model-free. Models can be used and may be useful, but it could learn entirely model-free, can adapt to changes in the way the building behaves, the building is utilized, and it has at least the potential for transfer learning from one building to others. But big drawbacks are clearly the requirement for a lot of training time and samples. We heard the sample efficiency term used several times today. One term not used today is the problem of initially unstable exploratory behavior that RLC agents show in the beginning, and how can we avoid those? And so this sets the stage for the research goals that we're presenting here. So this diagram presents the high-level overview of the research on RLC. At the top left, we have our advanced controls testbed that we are trying to, or that we have developed for this purpose. And we're testing out several approaches, as mentioned. And these approaches that are kind of grayed out on the lower left here, in the end, the goal here is to derive guidelines that bring us closer to overcoming the last mile into buildings. Zoltan and I are talking a lot about this. How do we make it into buildings, right? The ivory tower is very comfortable for us, but I think we should be, showing our true colors and see how can we quickly, that is within this decade, actually make buildings better and not wait until, someone solves these problems for us. So the algorithmic improvements, the speed improvements, all these things are, I think, important, but really, how do we get to adoption? How do we get to acceptance of advanced controls? But if we do, hopefully we can get into small, medium, and mixed-use buildings, learn from them, and the data we get would allow us to improve our research and improve our methods. And so with these guidelines then evolving, then maybe we are reducing the adoption risk for new building owners, and they say, hey, sure, well, if two others have tried it, I'll be the third, and then the 11th person will not have much less risk to take on. And so now, hidden behind this panel on research are some things that Shurav will present here today. Some work on offline learning, some work on online learning, hybrid approaches, transfer learning. So a lot of things, but the ultimate goal is to derive guidelines and then make it into buildings. And today we're going to, or he's going to present 4 methods. The first one is imitation learning, in which we use offline teaching to imitate very simple rules that we know and we can write down. And then the agent would improve online. And this imitation learning is expected to reduce training time and avoid some of that unstable initial behavior. Thibaut mentioned the ability to extract meta models, LTI, linear time invariant meta models from data. These meta models will allow us to initially explore the state space as described by these meta models. But again, that requires engineering effort, and the data we have may not allow us to build a meta model that's fully representative, because we have constrained observation data that only observes a limited portion of the state space. And an inaccurate model may again lead to unacceptable behavior. The third method is offline teaching from observed rule-based controls. So here we're learning from existing building data. Here, a limitation you will quickly see is that the state space is, again, insufficiently explored. We need to augment the data. We just heard a talk on data augmentation, and it leads to inaccurate value function estimation. This leads to inverse reinforcement learning. And in inverse reinforcement learning, the system learns an arbitrary reward function, and that reward function is then extracted and would explain the actual implemented rule-based control that we're observing. So it is inversely learning the reward function. This then has the promise of reducing training time and avoid some of the unstable behavior. So I would say at this point, I'll transition to Shurav if his voice is cooperating, and he will quickly tell us. Perfect, I hear you speak. And tell us, what's the use case?
Yeah, thank you, Gregor, for presenting. I have a bad cold. Sorry for that.
No. So, we're sorry for having you talk anyway.
Yeah, so the use case is a small office building located in Chicago. It has 5 zone buildings. So it's based on the DOE prototype building. So it has a gas-fired heating coil and a single-stage direct expansion cooling coil. So we considered an occupancy schedule from 6 a.m. to 10 p.m. And so the scenario that we are looking is a cooling application, and we chose an episode of a 1 weekday. And the DR event can happen randomly between 3:30 p.m. to 4:30 p.m. and can last between like 2 to 3 hours. So this is a demand limiting program that we are used. So then we move on to our imitation learning approach, which utilizes the rule-based data. And RL agent is initially taught directly to mimic the rule-based actions. And Gregor, one click. Yeah. So we are here, we are optimizing for energy consumption, thermal discomfort, and the demand charge cost with our on-off cooling coil action. And then we are repeating that to the 5 zones. And next, we compared this approach. So the rule-based actions were just simple. It was just to turn the cooling coil if the zone temperature was above the set point, and vice versa, switch it off if it's in the thermal comfort zone. So during a DR event, the cooling was turned off and the cooling was turned on 2 hours before the DR event. So that's the rule-based actions. And so we let the RL agent to imitate the rule-based actions. And so we utilize a reinforcement learning agent, which we call the PPO. So we perform the supervised learning where the actor tries to mimic the rule-based actions, and we pass that to the RL agent for the interaction. So it learns online, and okay, can I go back one slide?
Oh, sorry.
Back.
Yeah, I am. Mm-hmm.
Yeah, so the top chart shows the progress. So we compared this approach to the one without imitation learning. So it's a 7-day mean cost where we perform pure reinforcement learning and the one which uses imitation learning. So if the imitation learning is the red one. So we can, as we can see, we can avoid like 380 days of training with using imitation learning, and so it kind of reduces the training time. So that's really good. And next we train that for again another 100 episodes of the day, and we see some progress. Like we started at an average cost of like 800 per day, and which reduced to around like 750 after further interaction. So that was some improvement where we reduced the training time as well as improved the learning stability. Yeah, so these are the results of the 5 zones. And as you can see, when we compared that to the one without imitation, we had like a 8% improvement in cost using the imitation learning technique.
Yeah, I want to be self-critical here. This is again 8% is nice, but it's not earth-moving, right? Here we have this issue that with this effort we see fairly small improvement on this method, right?
Yeah, that's true.
Mm-hmm. Okay.
So the next we move on to our next method, which is the meta model extraction using the Info-SID algorithm. So we use the same rule-based data and we extract a meta model from this limited data. And as you can see, the meta model extracted has, so we compare that to the real building response. And as you can see, it's not really accurate, but still it kind of follows the pattern. And so we use this meta model to train the reinforcement learning agent beforehand. So it's kind of a pre-training, or if you want to call it offline training, before it interacts with the real buildings. And the right-hand side shows the training progress of the meta model with the training progress of the reinforcement learning agent with the meta model. So this is how it performs at episode 2, as it doesn't know anything. Gregor, back one slide. Same slide. Episode 2, it doesn't know anything. Then in episode 50, it kind of knows how to bring the temperature within the set points. And at episode 50, it's performing a little bit better. So this is the training progress that I show here. Next slide. And this is where I compared the performance of the offline learning approach versus the meta model approach. So the offline learning approach uses just the rule-based data, which is very limited. So we train two agents, the soft actor critic and the DQN agent. And as you can see in the top plots, the DQN and the soft actor critic perform horribly with these limited data sets. So we come to the conclusion that just training on rule-based data is not enough and leads to inaccurate value estimation, and so they do not perform well. In the bottom plus, we show the ones which has been trained with the meta model, and then we test that on some unseen training days and see how it performs. So it performs pretty well with the meta model training. Next slide. So now we move on to the inverse reinforcement learning approach. So in a normal reinforcement learning approach, we have a reinforcement learning agent interacting with the buildings. It's like a pure reinforcement learning agent. As we have discussed before, that it's not very practical. So that's why we use the use the building data from which is the rule-based building data, and we perform an inverse reinforcement learning process on that, where we kind of extract a reward function from this rule-based data. So this rule-based, so the reward function that is extracted kind of explains the rule-based action. So it kind of assumes the rule-based actions are optimum and extracts a reward function according to that. And so we utilize this reward function to generate Q values, and we then perform a supervised learning where we train the neural networks to have the Q, to learn the Q values and then transfer that to the DQN agent. And then we do kind of like an online learning with that. So yeah, so there are three processes with that. So first we do the reward function extraction. Next we go to the knowledge transfer, where we do a supervised learning. And the next one is just online learning with forward reinforcement learning, where the RL agent actually interacts with the real building. Next slide. So this is where we compare that with the same rule-based data that we had. So with offline learning, it was performing horribly, as I showed before. But with the inverse reinforcement learning, where we extract a reward function, and we see that it performs really well. Still, it wasn't able to write out the demand response, but like the demand limit, it was cooling unnecessarily, but it was able to bring the temperature within the thermal comfort bounds in its first interaction. So that's really pretty good. And in the next slide, we show the performance of the pure RL approach versus the inverse reinforcement learning approach. So then we let the RL agent that uses the reward function extracted from the inverse reinforcement learning to interact with it, to interact with the building like after like 100 episodes of a day. So it trains for 100 episodes. And so we see the performance on a test day, and we see that it performs really well. Here we show the inverse reinforcement learning progress on training data. As you can see, with the pure learning approach, it has a higher cost as it's very unstable. But with the inverse reinforcement learning, it starts with a lower cost and it's very stable, and it also outperforms with the pure reinforcement learning approach. So it kind of, so in the benefits is that it kind of like mimics the expert demonstration and improves on that. It scales well to environments with slightly different dynamics, and it also kind of prevents the unstable behavior, early initial behavior, and starts with a decent enough policy at the beginning. And it also significantly reduces the training time. And it and to be honest, when we tested that on a test unseen day, it had like a 32% reduction of cost compared to the baseline.
I think we go. Yeah. Sure. Can we jump to the conclusions?
Yes, so this is how we show the how it's performed, all the the improvements. So we have in the conclusions we have the four approaches, where we have the imitation learning. So imitation learning kind of depends on state action mapping with a reward formulation, and can also work with artificial data sets. So we do not need any data. We can just develop simple rules and can train supervised learning and pass that to the RL agent and that RL agent can improve upon that. But there are limitations on that, like the progress is around 8% or to 0%, something like that, as Sharath showed. It's not much improvement. So next we have the meta-model learning. Meta-model extraction is often difficult from building data, as they may not be accurate. It's only beneficial if the extracted model data is accurate. Offline learning with limited rule-based data is insufficient. As I showed the results, they were pretty horrible. Inverse reinforcement learning has we can work with limited data sets. So it's kind of a hybrid approach where with an offline and online approach where we extract a reward function offline and interact with the building online. So they were pretty effective in reducing the training time, and the learning progress was pretty stable. But it needs a state transition matrix, which is difficult to form. And I had to utilize a discrete state transition matrix, and it suffers from dimensional complexity, and the implementation is tedious. So this works best out of the four approaches that I tried, even with limited data set and incomplete state transition dynamics. So our next direction is to investigate the use of inverse reinforcement learning with state-of-the-art RL algorithms like soft actor trading. So here we only use DQN, but we also want to use imitation learning and also use continuous action space, which is one of the limitations of DQN. So that's the new that's where we want to head to. Well, that's it. That was our presentation. Any questions on that?
Thank you, Saurabh.
Sure, thank you. I think this should work this way. You made it. Thank you, Kuldeep, for the feedback. I'm wondering if. And I'm hoping maybe we do this at the open discussion later on, or the panel discussion, but are there reactions in the room about, are these the right steps to make reinforcement learning more implementable, more practical, lower some of the entry barriers that we are seeing? Or what's the audience perception on that last mile question? And where does RL stand in 2002? I think my first reinforcement learning paper is about 15 or 18 years ago, and I think I implemented reinforcement learning using tabular Q learning in a large commercial building in Omaha. And how much further are we 20 years later?
Yeah. I think Hafiz has some comment. Hafiz, would you mind just?
Hi, can you hear me?
Yes, Hafiz.
Hi, Gregor. I'm not sure if you remember, but I was in the DTU summer school with you. So
yes,
happy to see you again.
Happy to see you again, exactly.
And very interesting presentation by Gregor and Saurabh. Really appreciate the work. Actually, I have a question about the IRL, like the inverse reinforcement learning technique, which Saurabh presented. So I was wondering, like, how many test cases could you make the agent to learn the reward function for? Like, because when we talk about buildings, I guess it was a question from someone in the audience as well earlier, that how can we emulate extreme conditions of building energy management, or let's say buildings energy conditions? So how do you simulate like different cases for the inverse reinforcement learning? Like how much could we pre-train effectively? How could that go? And then we are sort of on a same level as we could do pre-training using some other techniques like, I don't know, like simple data augmentation using offline learning or something. So I was just wondering, like, how can inverse reinforcement learning work if the test cases are not like really extreme? Let's say, how can we make sure to do that?
Okay, can you explain a little bit about the test cases? What you mean by that? Like, can you give an example?
I think what Hafiz is getting at is how can we pre-train on non-extreme, more common scenarios, and have some level of certainty that on extreme days the system still behaves well. Is that
exactly.
a fair?
That's a fair explanation. Thanks for that.
I think you're touching on a philosophical problem. Is the problem of can these methods extrapolate well to and maintain decent behavior in completely new scenarios? And I think that how can we embed enough constraints so that the extrapolation is to those scenarios is reasonable? Wow.
Like, I mean, how different is it from simulated data training, like using inverse reinforcement learning, and then if you could simulate the data in an environment, like let's say Modelica or something, like you make an ideal simulator, like pre-train the model, and then you put the reinforcement learning agent into the real building. Like, how different is IRL from a simulated training offline?
So the reward function extracted has a bias towards the rule-based actions. So initially it will try to follow the rule-based actions initially. And then after interaction, it will try to change its behavior. So that's the thing. It's so initially we would have some rules which we want to follow. So it's kind of like an indirect imitation instead of like a direct imitation. So it's a very different process from the direct reinforcement learning approach. So you should have some rules, and the rules, and you should have some data, because inverse reinforcement learning, you need some transitional matrix as well. So what I did is that I made some transitional matrix from the rule-based data, which was incomplete, I agree. And so that's why it wasn't perfectly mimicking the rule-based actions. But it had a higher weightage. So initially it was trying to follow the rule-based actions. And but if you only train that with offline data with rule-based, so when it went to an unseen state, it became unstable. But in the inverse reinforcement learning, it somehow maintained the temperature within those bounds, as you can see.
Yeah, okay. That makes sense.
So so that's a pretty much advantage of inverse reinforcement learning. So it extracts the underlying Q value, whereas with the direct imitation, it's just a state to action mapping without any value function extraction.
It's actually pretty interesting. That's why I was just asking, like, what's the use case? Okay, thanks a lot.
Yeah, and it's pretty tedious to implement. So yeah, there's a lot of things that I did which I didn't mention here, but if you are interested, we can talk later on.
Sure, thanks.
Yeah, I'm sorry to interject in between. I think we have some time reserved towards the end in the form of panel discussion. So thank you, Gregor and team. Thank you, Saurabh. So let's move on to this remaining presentation in this session. I think both the presenters are present in person. So the first presentation is B2RL, an open source dataset for building batch reinforcement learning. So that is another interesting approach, and we would like to hear about that. So the presenter is Xin Yu Liu.
Hi.
Over to you.
Hi, everyone. I'm Xin Yu Liu from University of California, San Diego. I'm going to present our paper, B2RL, an open source data set for building batch reinforcement learning. So first, an introduction and motivation of our work. So batch RL is a data-driven method where we have existing data generated by some unknown policy, but we may not have a simulator of the environment. And as we can see in the animation, that batch reinforcement learning is also called offline reinforcement learning, where we only learn from the logged interaction, which is a static data set. During the training, we don't have to interact with the environment, so we don't need a simulator of the environment. And online RL has to learn from scratch, from randomly initialized policy, where for batch RL, we could learn from existing policy. For example, it might be rule-based policy, MPC policy, or even RL policy. So there are already various applications of batch RL in different fields. But currently, we don't have a standardized data set for building BRL learning. So we hope our data set could provide a fair benchmark comparison and avoid running benchmarks performance for building experts to achieve fast prototyping. And here is the experimental setup of our works. So in our paper, we have two sets of buffers. One from the simulation environment, which we use SIGEnergy as the environment to do the simulation. And the other one is from the real building, which is our UCSD CSE building. We extract the data from the database. So for the simulation environment, we first train 3 behavioral agents with quality of random, median, and expert. Then use them to generate buffers for batch RL to learn from. And for real environment, we extract the data from our database and pre-process the data as the Markov decision process transition. So the BRL agents could learn from it. And for the real environments, the existing policy is the rule-based control policy. And here is the RL setups of these two environments. So there are 20 and 4 dimensions in states for the simulation environments and the real environments respectively. And the action dimensions are both 2. And as mentioned before, the simulation environment is the SIGEnergy energy plus 5-zone building with 3 different weather conditions, hot, cool, and mixed, and 2 different type of responses, deterministic and stochastic. Sorry. And can I stop the? Okay, so and for the real environment, there are real building rooms or zones in UCSD CSE building from 2nd floor to 4th floor. And the reward function of these 2 environments are pretty similar. They're both a linear combination of the energy consumption and the occupant's thermal comfort. So for the real building environments, the compared algorithms are the state-of-the-art batch RL algorithms. The first one is the batch constraint deep Q-learning, BCQ. BCQ is a model-free RL method that mitigates the extrapolation errors induced by out-of-distribution actions selected out of the existing data set. they demonstrate that the traditional off policy method has diverged extrapolation errors to learn pure offline. And they are one of the pioneers of the batch reinforcement learning. And the second one is the BEAR, bootstrapping error accumulation reduction. It mitigates the bootstrapping error by searching over the sets of policy that is akin to the behavioral policy. And the third one is the PQL, pessimistic Q-learning. It uses pessimistic value estimation in the low data regions, in the Bellman optimality equation, as well as the evaluation backup. And the details of the experiment is that the buffer size range from 170 to 260K for each floor. And for each floor, it consists of 3 to 4 rooms, which is an entire year of data. And each time step is around 10 minutes in real time. And the learning curve we see here is the entire evaluation period lasts for about a week. And it is averaged by six rooms in 3 floors. And also we break down the optimization objectives in this figure here. So the default rule-based energy consumption is normalized as 1, and we could see other methods, how it performs. And the thermal comfort, we use the PMV, predicted mean load, as our metric. And here we're showing the absolute value of PMV. And the compared algorithms for the simulation environments are TD3 plus BC. The first one is TD3 plus BC. It's an offline version of TD3. It simply adds a behavioral cloning term to regularize the actor policy towards the behavioral policy. And the second one is CQL, conservative Q-learning. It's derived from soft actor credit. It learns a lower bound estimates of the value function by regularizing the Q values during training. And the third one is a behavior cloning model. So we simply train a VAE to reconstruct action given states and simply imitates behavioral agent without the reward signal. And the experiment details is that our buffer size is 500K and one episode is 1 year. It contains around 35,000 time steps. The entire evaluation lasts for around 14 years. And the quality of buffers are expert, median, and random. So
sorry guys, the TV just suddenly shut off. Can you hear us?
Yeah, we can hear you.
Okay.
We just lost the screen.
Yeah, the TV suddenly shut off.
Oh.
Oh.
For that.
do I need to share screen again?
No, it's,
okay.
I think, yeah, can you guys see the screen?
No, I think you should share it again. Unshare and share.
Oh yeah. All right, now.
Yes.
Okay. 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 So. Okay. So the expert buffer is that the behavioral agent is trained for 500K time steps and use the pre-trained agent as the expert agent to generate buffers. And median is that we train the agent half the performance of the expert and stop training and use it as the agent to generate buffers. And random is the randomly initialized agent. Oh, sorry. And in the table here, we could see that we summarize different buffers with different weather conditions and response types. So we can see that CQL outperforms others in our experiments. And here are the learning curves that we learn from the expert buffers. So we have also shown the dotted line as the rule-based control policy, and the dotted purple line is the expert buffer performance. And we compare with this state-of-the-art methods. So here are the conclusion and discussion. So we're the first to open source the building HVAC data set for batch RL learning. And our data sets consist of one of the real building and the other with simulation environments. And our goal is to encourage building experts to explore the opportunities for batch RL. And with the standardized data set and state-of-the-art algorithm scores, researchers could save the efforts generating the data set and running benchmarks. And our future work is to expand our collections with various environments and most recent batch RL algorithms with different building RL frameworks. And thank you for your time. And I'm also looking for opportunities, maybe internship or full-time. Feel free to contact me. And these are our co-authors.
Nice. Thank you, Shin. I think that was very good presentation. I would like to open the floor for one question, one or two questions. Matthias, any questions from in-person attendees?
No, not for now.
Okay.
Thank you.
Okay, so yeah, let's give a round of applause to our speaker. Our next speaker is Dr. Matthias. He is going to present a framework called ComfortLearn, which is enabling agent-based occupant-centric building controls. So Matthias, the floor is yours, and we'd like to hear what you have.
Thank you. I just realized that this is maybe blocking. Okay, awesome. I know maybe we're a tiny bit behind schedule, so I'm gonna try to make it short and sweet. Good morning, everyone, or afternoon, wherever you guys are. My name is Matthias Quintana. I just finished my PhD a couple of weeks ago, and I'm a postdoc currently at NUS. I'll present you my framework, ComfortLearn. So regardless of the goal of reducing energy, as we all know, I think we're all aware about reinforcement learning, as we just talked about, and the strategies are related to energy savings and whatnot. But sometimes we know that occupant-centric itself, we tend to call this field like that, but we use a lot of tools that can be quite very specific or sometimes niche or hard to use. Luckily, we've seen a lot of effort in open sourcing these tools or making these tools more available via intuitive UIs or just proper documentation so we can all correctly use them. But nonetheless, they still sometimes act as gatekeepers for other communities that might be interested in our field. Communities or researchers that might not have that domain expertise or knowledge. On top of that, besides all of these things I just mentioned, actual occupant data is rarely used in the problem formulation for controls. In fact, thermal comfort is most of the time used as a PMB calculation or a proxy of that. But there's documentation saying PMB, based on the Azure Comfort database, it's only accurate 1/3 of the time. Other times, thermal comfort is assessed as a fixed temperature range, and the RL strategy is focused on maintaining set point on that particular band. All of this leads to a lack of standardization or standard ways of comparing these different control strategies, which in turn, it's a lack of a realistic portray of how occupants will feel inside these buildings. This is why I decided to propose and develop ComfortLearn. So this framework bases is in agent-based modeling for occupants. It uses empirical data sets alongside that can be used alongside control strategies that could exploit this. Basically, additionally, it also standardizes the way these strategies can be benchmarked. First, we can take whatever model we have for the building. We can, if you want, use those other cost simulation tools or even data-driven ways for having that dynamics of the buildings. There's evidence showing that we don't necessarily need a high-fidelity model for control purposes, we can have good enough approximations. And with that in mind, we don't need expensive cost simulation. We can get by with just pure approximations, and therefore not other software is needed other than this OpenAI environment. On that note, another flexibility is that having more OpenAI environments that could standardize and help us more leverage the playing field for all different strategies could definitely give us a broader, help us achieve a broader range. Now I'll show you exactly how ComfortLearn works. So first, we have different streams of data. We have primarily occupant data. We have the building historical data. We have some weather data. Now, more realistic, we can then produce models for both the occupant and the building. For the building, we can do many different things. We're going to focus primarily here on the occupant. Because we're relying on empirical data sets, we're going to have a more realistic scenario of both. And finally, once we have the two models, we can proceed to a normal RL setup. We can define the number of steps we're going to do, the actions, the rewards, and whatnot. But now let's emphasize exactly this portion. How are we going to model the occupant using agents, agent-based modeling, and exactly how is that empirical thermal comfort data is going to be used? So agent-based modeling, for the ones that may not be familiar, it's all about generating virtual entities, in my case, occupants, as autonomous beings that have certain behaviors, actions, and states. That way, by generating different types of these occupants, their effect on bigger systems or contexts can be understood. In the context of building control, I chose the behaviors to be moving around different buildings or different zones. Then their state is the actual thermal preference. This can be obtained from an empirical data set. And then to keep track of their preferences over time, I decided to go with exceedance, a cumulative index as an evaluation metric. This metric has been used before in lighting control, and it satisfies the guideline requirements set by the occupant-centric control community. This value is calculated by dividing the time spent in uncomfortable conditions by the time the occupant was in set room. Now, let's dive into exactly how then the data set is used with this approach. So let's say here it's a real data set. You can find the link later down in the presentation of 14 occupants in a tropical area. Now, we're all aware of the different factors that affect thermal comfort. However, in this distribution, I'm only showing you the thermal preferences based on indoor temperature, because it's the one factor that affects the most and can be easily obtained in many buildings without deploying new infrastructure. With this, we can generate different entities, different occupants, and then at any indoor temperature randomly sample what the preference label might be. But how do we generate different profiles, right? This is one shape of distribution. How can we have multiple ones? We'll introduce sort of a knob or a parameter that I call tolerance. Now, tolerance here is not a generalization of how occupants might feel. It's just a practical setup or knob that can help us generate these different profiles. And in ComfortLearn framework, I define tolerance as the percentage of comfortable or no change responses divided by the total number of responses. For example, this is the original data set with all participants. What if now I want a profile of participants who only have 60% of their votes as no change? This would generate this other distribution. So now we have two different distributions from which we can generate these fake participants or virtual ones, and we can place them in these rooms or buildings and see how they react to the building running as is or different ways of using the buildings. For example, let's say if temperature is 28 Celsius inside, occupants that come from distribution on the left will have most likely feel no change, whereas occupants who have a preference distribution on the right with a tolerance 0.6, they're most likely say they'll prefer cooler. And by basically sliding this knob of tolerance, we can have again multiple profiles, and we can have this plethora of virtual agents and see how they behave. In order to prove this, to put this into a test, I decided to run this in a case study. So in my case study was two different zones in educational buildings in Singapore. Zone 1 has air conditioning and fans, so it has a higher temperature set point, and Zone 2 has purely air conditioning. This is in the tropics, and so set point is already a little bit higher than normal, but the data set that's going to be used alongside was also collected in the tropics, so both do match. Now on the right, we see a week worth of the historical indoor temperature for both zones. Sorry, the color bands for each zones are plus or minus 1 Celsius for the respective set point. Now, in most occupant-centric control strategies or approaches, these bands will be seen as comfort bands, right? So the goal will be to keep set point between these bands, meaning that as long as that is true, people should be okay. So by that definition, if you look at this image, occupants should be okay 93% of the time. That's the time between 8 and 5 that the set point remains in this band. But does this really happen when we use real data of people that were under these conditions? To test that, I generated 10 virtual occupants based on the empirical data I showed. I decided to place them in these rooms, virtually place them, and see how they will react in these two slightly different rooms. Here, we have a heat map that shows the overall exceedance. Remember that the lower, the better. For occupants with that tolerance knob set to 0.6. Now, the darker red shows that these type of occupants are comfortable 40% of the time on average in Zone 2 throughout that whole week I just showed. And on top of that, it looks like Zone 2 seems to be a slightly more comfortable space, at least in thermal preference wise, than Zone 1. But what if we have what if we compare two different profiles of thermal preference based on that knob tolerance? So here's the time series of the exceedance value throughout that week for the virtual occupant 10. So the thick line is the mean exceedance value, and the shaded region are 2 standard deviations after 30 trials. Now these figures confirm that for tolerance 0.6, Zone 2 is a better environment for these type of occupants. But for occupants with a tolerance 1, Zone 1 is a more suitable space. Again, this is all based only if we look at this particular empirical data set under this, within this building. And in fact, with an average exceedance value of 0.25, occupants from this data set or behave like this with that tolerance are comfortable 75% of the time, which is not what the initial metric, that common metric of the comfort band told us. That was an overshoot of 93% compared to a more quote-unquote realistic 75%. So in summary, ComfortLearn, I show you that relying on these static metrics like comfort band can be misleading, and really bringing the human into the loop, bringing the human data, empirical data into how we evaluate and we compare algorithms, gives us a more realistic picture. I designed ComfortLearn basically as a simplified frameworks that will minimize the use of these cost simulation tools of other quite computational expensive tools, but it can be also appended to those if you want to. This framework does allows us to emulate a range of comfort outcomes. As you see, we can have a plethora of comfort profiles and many of the other building control strategies. I just show you the building as is with the historical data, so we can go and play even more. But now with ComfortLearn, all these wide diversities can be set because it's not just unique to these data sets. It's designed in a way that you can bring your data set and set it up that way. So the temperature preferences I show you are just because I decided to use that one tropical thermal comfort data. But of course, if you can bring your own that matches your season, your tropical area, or your location, that might be even better. And you can that is the actual GitHub repository for the tool. We do have the dataset we use available right there, or the link to the dataset. That's my contact information. And thank you so much for listening. Apologies for the kind of rushing thing. Thank you so much.
Thank you, Matthias. Are there any questions?
Yeah. Oops, I need to raise my hand, right?
No, go ahead, Gregor.
Okay, Matthias, thank you for your presentation. In a room full of people, does everyone need to have a smart device on their wrist? Or can I have a subset and still learn something about the population statistics?
So that's a good question. So we do have a paper regarding that. It's not really in this work, but I can talk to you offline about a work related to that. Here, we're not necessarily addressing that here. Yes, we assume that everyone was able to provide their comfort individually, but there are efforts that show that we might only need to know the preference of a cohort, of a cluster, instead of every single person.
Perfect. Yeah. No, I'm asking because I love my mechanical watches, so I'm not going to get one of those.
Understood. No worry. I get it.
Hussein, please ask your question.
Hi. Thank you, Matthias, for your presentation. So I have a question, like, in order to learn the behavior or the preference of one occupant, for example, how much data did you need for that, or how many days of learning did you need for that?
Oops, I'm sorry. That's a good question. So I think I messed up the slides. So in the particular data set we had, that I used for this, we had at least 50 data points per person. And there have been work by, if I remember correctly, Joyce Kim from that time UC Berkeley and now Waterloo, that sometimes you need as low as 30 data points to have some sort of okay-ish personal model and have some trend of comfort. But I think as long as some historical thermal comfort data is available to you, I think that sweet spot is around 50 or 30 to 50 or something like that.
Thank you.
Mm-hmm.
Thanks, Matthias. I think in the interest of time, we can proceed. So
sure.
Those were the last two presentations of session 2. The next thing that we have in our agenda is short break, and then followed by a panel discussion where we get together with our keynote speaker experts and all of us. We will discuss few interesting, challenging questions. So I think let us reconvene exactly after 5 minutes. Let's take a break and then we can start with our panel discussion.
Thank you, Kuldeep. Thanks to the speakers.
Thank you. Thanks all.
So the survey for the purpose of the tool, since I was doing the temperature, I decided to standardize the parameters, but only these responses that were in the room indoors, much, but only this. So that definitely brought down the number of available samples. It's still around 30. Yes. It was for your office building.
Okay. So why, like, in this room, and different people have data, and how can you assist with the control of this?
So that's a good question. And with this tool, we're not necessarily trying to solve that controlation, right? We're just trying to at least let the control people be aware of, like, you have to use real data. Try to account for the differences, right? To at least be aware that there are the differences. So trying to fix that set point for everyone might not necessarily get the job done.
Okay, so how frequently the occupancy response to this?
So this data was collected once every hour.
Every hour.
Yeah.
But during the occupant hours.
Yes, from 8 to 5. Yeah. When we found in other work, this one was that for that sort of like diverse preferences was that it kind of helps where you can foster people in these preference groups. Right. And you don't necessarily care for them. So instead of there's 10 people, right, you don't care about 10 completely responses, but maybe there's only 2 groups. So it might be hard, so like 2 preferences to worry about, right? There's definitely cases where both like are opposite. You may need to stick with my order too. We're not there of how to solve that. Right. But going from 10 choices to 2 at least, one step over. Yes.
But are you considering for the institutional reviews?
We might. Well? Yeah, actually the next step for this particular tool, we're looking at campus level, like urban level, have like Wi-Fi data for mobility. Right. So we're doing agent-based modeling, on a campus level, see how people move between buildings. Right. And what their content might be, and how the decision might get there to like go to other buildings and so on.
So the experiment, the data that copies in the SB office.
That one, into buildings before in other buildings.
Oh.
Like an air conditioner and really small things.
It's like all the researchers.
Mostly, also the students are. You know about it before?
Because I graduated from the US.
Oh, okay.
For my
Yeah.
bachelor.
Oh, okay. Yes, right? No.
If you're back.
Oh, okay. You teach that.
Oh, really?
Yeah, yeah. Try to you teach that.
Yeah, I'm African.
Okay, okay.
I graduated from the second one.
I see, I see. Awesome. We have a different gallery here.
Yeah.
You met her?
Yeah, that's where I heard.
Oh, okay, okay. Oh, nice. Yeah.
Nice to meet you.
Nice to meet you.
Very nice.
Thank you. Thank you. Oh, yeah. Thank you.
So you mentioned lack of observation that may not be some of the very stuff.
Oh, well, maybe because I kind of so I don't want to like do that.
Yeah,
and I know I've seen some.
And this for learning the training of the agents.
Yes, for the control purposes. So in order to away from that, I've seen some work in some areas that to for the building because fascination is of having all the nuances of how the building reacts, right? If you have some data model that can be good enough to then do some interactions, see what's it.
I mean, I guess I think we have discussed a little first how good is what's your metric design. Okay, this is good enough. Is we don't work on that.
We have not actually. I don't have any change. But that's more than that. And I didn't went too much into that. So that's yeah, all the rest of it.
One case student, one year.
Right, and there's no issue.
Also, like you said, you mentioned in the morning was like we're building models separately, the common separately. Why
so and this is also because well, the model is just because of both
shouldn't feed into the building process.
So the room is measured.
Yeah,
it does.
Okay.
So I have and then we go see this. Exactly. Then we just keep track.
I think we can give a minute or so.
Yep.
Then we can start.
Let's get all our seats, virtual and real. Oh, I had my coffee somewhere. One second. Okay.
We can start.
Do you want to start, Kuldeep? Yeah. Mm-hmm.
I think I'll wait for Gregor also.
Yes.
Yeah.
That would be useful.
Yeah. Thanks to Troy. I think it is very late.
Yep.
Being up with us.
Know that there's some other people in the Asia Pacific area, so
yeah. Hey, Gregor.
There's Gregor.
Yeah. So, Matthias, do you think we will have people coming in person? Should we wait?
I can try to call them in if you want.
Yeah, sure.
Yep.
So Troy, I hope that we can our paths can cross in Salt Lake City. That's the plan for early December. We're currently trying to plan a visit, or I'm trying to come out together with Laguna, and hopefully we can find a day that we can meet together in December.
Oh, that would be awesome.
Mm-hmm.
I recently had a nice panel discussion with Draguna, and we had dinner afterwards, and we were able to talk through a bunch of these topics. And so I think there was actually a question here that's I'm kind of eager to get back to, because it reminded me of a point that Draguna. So
please, yeah.
Yeah, we can start with that, Troy. I think that's good. Let's, when we get a thumbs up from Matthias.
I tried to call them. That might be on the way.
Okay. Let's wait a
Yeah.
minute and then start, because I think also lunch will be served on site there pretty soon, and so that might, just not
And
help.
we're losing them, and they're gone.
we're just losing them. And then also, yeah, we're a bit ahead of time. I mean, over time, so we may extend 10 minutes or so, but then not too much. And so we'll of course want you try not to be up for nothing, and at least drag some knowledge out before we let you go. Yeah.
So
okay, go ahead.
I presume Zoltan, you were hoping to have a set of questions, as I know you're excellent in guiding conversations. But can I interject and say, this is RLEM’3, right?
Mm-hmm.
Do you see what are some of the developments you observed just over the short time span of 3 years of running a dedicated workshop on energy management and the opportunities that RL has in that context?
I mean, I think this is a very good question. I actually tried to summarize that in my head as figure out some sort of a conclusive comments after we finished. But I think one of the trends that we noticed, I don't know if this is by design or because just where things go, that over the time of the last 3 years, the direction has been a lot towards real world RL applications, demonstration projects. I think there was very clear last time we had one dedicated session on implementations, which I think is great. And so, the first time we did it 2 years ago, what could you expect? I don't know. But all of a sudden, like 80 people showed up. I'm like, okay, this was unexpected. The second time, yeah, about 40 or so. And then this time also roughly that stage. So I think we're converging on that sort of number that is reasonable for this group and generating some output. I think over the last 3 years, and I don't know if I don't think this was because of RLEM, so I don't think we need to take credit, but there was a lot of development, right? I mean, you guys did ACTB, we did CityLearn, but there was Energym, there was Synergym, we had one presentation at the end. And so there's a lot of these developments that are happening in this direction. And so I think it's going where it should go. And so, but we are at this point where now we should be good to discuss where should we go. I think that's kind of like the purpose of this panel also. We hadn't had panels in the last 2 times. All the discussions were a bit ad hoc. But I think now that we've had this a few times and we've seen a few talks and we've done a lot of work, it's good to sort of like take a step back and see where we would go from here. So I think that's my conclusion.
Perfect. Okay.
We're on our way, but not quite there yet, I guess.
So you mean we have to come again?
Please, yes, you have to come back. Unless you solve all the problems, but in case you solve all the problems, come back to tell us, and then we close shop.
Well, I see Jan joined, so
Hey,
Jan
Jan.
and Zoltan as the chairs. I think you're now poking the audience, right?
Yeah, we're poking the audience. But let me kick you off. So one of the questions I had, because you showed in one of your slides, all the stakeholders, what the challenges, and when you asked for feedback, Gregor, right? Like this nice circle that showed occupants, and and so, but the way you presented it implies that they're all equally important, right? Do you have like a sort of like a ranking in terms of like your favorite stakeholders to poke to make this happen, or who should we poke? Because that's essentially our clientele that needs to be that needs to be told that this should be happening, basically. And then I asked Troy the same question afterwards. So what are your thoughts on this, Gregor?
I mean, having gone down several decades now trying to implement MPC, real-time MPC in buildings, I think it is the conversations with building owners and their fear of negatively affecting occupants, giving them assertions and the peace of mind that we're not making their occupants miserable. And I think we're seeing a lot of building owners that are very, very sensitive right now to further jeopardizing their lease agreements, because we've seen exodus of tenants out of a lot of prime real estate. We see a lot of condensation and compression. We see a lot of empty real estate. I saw during my time in Sydney, billion-dollar towers empty, waiting for tenants. And here we come and say, well, we're going to do something to your buildings. And if there's just the slightest hint of discomfort or annoyance, I think we're out of the building faster than we entered it. And so I think that building owner, and giving that building owner enough of a motivation to ponder something novel. And it, of course, needs to be someone who is dissatisfied with the status quo in terms of building controls. Well, if someone says it seems to work, it's keeping 75 degrees in the summer, why would I bother? And I think if we think of the 110, 100 or $3, $30, $300 often quoted situation, I'm not sure we bring enough to the table by saying we're going to save you money, right? That's just not going to turn their crank. And so we have to come with better arguments than saving cents on $3 a square foot if we are risking dollars on $300 a square foot. And we need to give them enough reason to make that jump into the unknown territory of non-PID based Johnson controls, Metasys and whatnot control. I think that would be my rank. That's number one. And from conversations, I mean, a common quote I get, hey, you can do anything you want in my building, just don't touch the thermostats.
Yep, that sounds familiar. Troy? Same question.
Yeah, so I probably have, we're probably a little bit unique here in that we get to talk to so many stakeholders, being in the market, not only on the market side, but on the strategic and investment side. And one of the things I think, PassiveLogic, when we were looking at this problem early in our development, we started going through all those stakeholders, and we said, actually, we think the most important stakeholder is the most forgotten stakeholder, and that's the contractor. And so what we found was that, in the market, 80 to 90% of the time, the contractors making the technology decisions, the building owners, these big REITs that maybe own hundreds of billions of dollars, often don't know anything about their buildings. They're financial institutions. And so that decision, is you're often like 5 to 7 steps away from the person who's actually making the decision. And this is actually Gregor made this really interesting point that I started this when we started PassiveLogic, we started with the same thesis. We said, well, you know, the market's conservative. This seems to be this like traditional wisdom we all had. And then we went out to the market to these guys who actually do the work. And we found they weren't conservative at all. They just didn't have any choices. And they basically can shovel BMSs pound for pound. They're all about, you know, relatively the same thing. You know, this one has a bell, this one has a whistle, but they're struggling under this like stack, this weight of all these problems that nobody's actually solved. And so what we found was, we think that the problem in this, you know, I think going to Gregor's point about the $3, if you're saving on the $3, I think too much of the industry, too much of the talk is about trying to save people ROIs. And I think the problem with that is that the vast majority of people just can't think that far in the future. And if you instead show them how you can save all kinds of pain points, you know, we take them through Autonomy Studio in an hour, and they're just like, holy cow, you showed me in an hour what takes me 6 to 8 weeks to do, instant like value, right? I'm going to give away energy efficiency, whether or not you care, right? Like, you don't have to care about energy efficiency. I am instead going to do these sort of like direct value points that are not usually what we as like energy engineers and engineers are first and foremost thinking about. These sort of grand vision of energy efficiency. It's like, it often starts at like, boy, here's this like just mire of pitfalls that Boiler Bob and HVAC Perry have to deal with on a day-to-day basis, and nobody's ever dealt with their user experience.
Yeah, this is such a good point. I heard the same comment when we talk about electrification of residential buildings. It's not you know, not the building equipment, not the equipment sellers. It's the contractors that put it in, that advise people. So it's really, if we can give them the tools to transition into an electrified building stock, you know, remove, exchange the gas burners for heat pumps and things like that. They need the tools so they can convince the homeowners. Otherwise, it's a pretty hard battle to do. That's a great point.
Yeah, if I may second on this, Troy, what you're basically saying is, if we give the contractors and the specifiers the choices, the better choices, then these technologies will find their way into buildings without any need for convincing them of their merits on other grounds, because they bring to bear so many benefits. I mean, the PassiveLogic tool chain, if I may call it, or ecosystem, seems to provide all that, as you said, that what you've accomplished in 1 hour. And so you're creating facts by convincing the technical decision makers. Is that creating facts in the sense that the next new building that you get in that has a choice between a conventional BAS vendor and PassiveLogic will choose PassiveLogic because of all these benefits, and you didn't even have to raise the issue of comfort or carbon or energy savings, right?
Or even AI, right? That we essentially just show them how they can install us, you know, N times faster than a conventional BMS. And at a similar price point. Oh, and by the way, you might care about this energy efficiency you get, but you're not buying that.
Excellent. Yeah. So when there's no convincing of the other usual suspects of roadblocks that you have to do.
Well, so then there's a flip side to that, and I think. So that's where we started. Now what's emerging though is all of a sudden we've had this sort of rush in of very large building owners saying, we either need to do something about ESG, which may not have been a term that most of you guys heard, you know, more than a year ago, but all of a sudden is top line. Literally a major REIT can't get investment for a new building unless they check every ESG box with their investors. And so now all of a sudden it's top of mind. And the more strategic ones are saying something more than like, how do we get energy efficiency necessarily, but hey, to your point, that $3, $30, $300, they're realizing, well, they might own hundreds of billions of dollars worth of buildings, but at the end of the day, it's like dirt and concrete and steel and drywall, and how do they make the transition towards a digital business, a business that they can start plugging services in that are worth more than any of those 3,300 that are like when they flow into that building, JLL would say that's 3,000. But they can't do that unless they actually have a digital platform that understands the building. And so for a lot of them, the outcome isn't necessarily even the control, but the operational like digital twin that comes out of that control that allows them to plug in other services.
Yeah.
And Matthias's last. Oh, sorry.
Go ahead, Gregor. Go ahead.
No, you were just mentioning yet another order of magnitude of cost or revenue. Then I must ask, will this involve the occupant at some point to a degree that we just heard from Matthias and this occupant-centric control? Because if you are trying to, you're suggesting higher value streams than just the salaries involved in placing people in spaces, but you are thinking about a digital platform that can enable much more, but then it must connect to the occupant. Is that on the horizon? Is that what you think is the?
I mean, that's in our system, with the digital twin, we keep those digital twins of all those entities, including the occupant. And I think Matthias's presentation was really great. You have to have that connect. There are multiple entities within a building, right? So it's the building as sort of the operational goals of that building of how do we get first and foremost the HVAC and then the energy systems going. That's a requirement for buildings, right? So that's why controls are so pivotal, because it's the place you can slide a digital platform in. But then it quickly becomes more about not just the things that are bolted to the building, but how do you also automate all the business processes, which inevitably might be, people, it might be logistics, it might be manufacturing, it might be, just getting all the catering on a daily basis to a tech company like PassiveLogic that feeds all its employees, and what's the current occupancy that day to make sure you're not either under or over, ordering. And those kinds of services, when you look at everything from your maintenance management services to your, the food services are this part of this living ecosystem, right, of what's going on inside that building.
Yeah, that's really interesting discussion. May I ask the question that we have from Greg Pollock in the chat?
Yep.
So I think Greg is trying to mention about building a new workforce. So he states that the aging workforce was mentioned several times during discussion, and many of us involved in educating next generation building scientists, engineers, and control specialists, right? But
yes,
having seen this changes, technology changes, paradigm shift in the control technology and approaches required for corresponding paradigm shift in building and control education and workforce. So how we keep up with building this new generation task force, considering the fact that this paradigm shift is happening in control technology? Should we be just keep teaching the traditional control sequence and delivery process, or should we ask our students or maybe employee to look more like a building data scientist? So that's, I think it's in the crux. I think the question is how to better build the next generation task force or workforce.
So as a controls educator, I take this on quickly. I teach building automation controls. Clearly that the way we've taught it in the past by learning how to translate sequences of operations to DDC code, that can't be it. And I think all of us in the education are adding at least data science and machine learning courses to our architectural building systems engineering curricula. And I think that's a requirement. But I think Troy said something that I hear and over again, which is that building controls vendors, building large building large campuses cannot keep or hire the kind of expertise. There are other industries that appear to be more attractive, right? That attract away the bright and the smart and the young and driven from the built environment. And it is, I can say I've been an educator for decades now, and it's interesting how even within my field, it is just hard to convince young people to see the value of working on energy and buildings. And even though we always quote the same 75% numbers that I started myself with, it's not enough of a crank to turn for students to say, I want to do this, but instead there's an appeal to let's be clear about this, to tech companies. There's an appeal to, I don't know, just computer science in general that attracts the brightest minds away from what I believe are societal changes that need the brightest minds. We don't need better click-through performance. We need better buildings. And
I will quote you with this, Gregor. I will make a quote and quote you with this. We don't need better click-through performance. We need better buildings. Like that's a great one.
Yeah, well, I'm a firm believer in that, and it's a little bit frustrating because I feel like, we had Stephen Chu, our former energy secretary under Obama, say, "Oh, buildings are these low-hanging fruit that just are waiting to be picked." And we have these stainless steel wires connecting these apples to the trees, and we're pulling, and we just seem to not be able to get them off the tree. So it does require really sharp minds, and we have them coming into our universities waiting to do impactful work. But at the end, Troy mentioned it, the companies can't hire these people to keep their current controls business going. And these are small numbers of students who choose to go into our programs, smaller numbers even that choose to go into controls. And what is missing? I don't know. So Greg's question is extremely pointed, because the workforce development is, I think, for this area, super important for the survival, or for the transition that we're all in. Maybe not survival, but for the transition that we're all dreaming. So I stop here.
Yeah, I'd say, there's two sides to this. One, we're very driven by democratization, that there is this already big workforce out there. For every controls integrator, there's 500 HVAC technicians. And they're not programmers, but they have an intelligence and knowledge about the physicality of buildings and how they go together, right? And so in many ways, sort of the digital twin approach is appealing to the people who know the physical structure of things, but they're not programmers. Now, at the same time, I think there's this thing that I've become aware of as we've gone through the process, is that what I think the problem is the lack, on the flip side of a tool like PassiveLogic, where you're making it both more democratizable, but you're also bringing modern technology to bear. And we have to face the fact that, it's just not very appealing to bring people into an industry where you're going to be like, hey, here's 40-year-old platforms, learn to do 1970 style imperative programming using 100-year-old algorithms, or you could go to Google, and it's like, that's not going to sell, right? So I think part of it is we're not bringing the technology that's going to be appealing to the smartest and brightest minds. And I think what we're starting to see as a company who is trying to acquire all those smartest and brightest minds, that there's an appeal external to these controls contractors and distributors when they see demos of what we're doing. They're like, I can finally recruit people to do this, right? And so that's the problem, is that we're just, as an industry, we're lagging. And I see ourselves very relative to the vehicle industry, where 20 years ago the vehicle industry was pretty damn boring. And then this cute little company, Tesla, came around, and everybody's like, oh, that's hilarious. They'll never do anything. And nobody's ever like taken on the big auto companies in 100 years. And here we are, right? And so I actually think what's interesting is that the building market is learning from that. And I think the acceleration, the changeover, it's going to be much faster in the building market because we've had benchmarks in other technology spaces.
And you think an otherwise innovation resistant industry might become more comfortable with the disruption, right? And because we've seen it in other
and that goes
domains.
back to my other comment is when I go into an integrator, and when we first started doing this, and our stuff was very raw and it was early, and we had NDAs in place, and we'd go to an integrator and they'd be like, oh yeah, fine, come talk to us. And you know, we'll give you an hour. And then they, like 90% of the time, they like hold us hostage for 3 to 4 hours. And they were so excited. And they were saying things like, you know, nobody's really walked through these doors with anything meaningful and new for 15 years. Like, kind of thank you. Like, and so we started to really understand the importance in technology inclusion, right? That there's this lack of inclusion that's been happening, that at the end of the day, the construction industry is driven by guys in blue jumpsuits that drive trucks, and nobody's really considered them before.
Yeah, absolutely.
Jan, go ahead.
Yep, I'm having next question. So this is connected to what Troy said about the need for new infrastructure and democratizing the tools for the community. My question is, how do we not repeat the past? Because the past legacy companies like Honeywell, Johnson Controls, they developed these BMS systems some decades ago, but they forget about interoperability, and they basically ended up in the competitive market. And now we are facing this issue like that is impossible to build a meta solution, so we need to start from scratch. And there is emergence of startups and new companies that want to do that. One of them like PassiveLogic. So what is the path forward? Like, are we going to emerge in a new BMS systems 2.0 where there is like a couple of companies, they don't talk to each other, nothing is integrated, there is no interoperability? Or are we going to see one dominant player, or are we going to see the consortium of tools?
Yeah. Well, I think we have to like take a look at where do we get value from community, and where do we get value from single company innovation. And I think for instance, if you look at Linux as an example, is like not everybody had to go develop an operating system. At some point, operating systems were an interesting like field in the early 90s, but at some point it's like we all needed just an operating system. We didn't need to make a lot of them. And so, but yet in that same space, we've also seen that there's the lack of, in the Linux space, that there was never really this mythical emergence of the Linux desktop for the average person, right? And that's because there wasn't the desire to sort of innovate at that level. So I think where we see it is, where can we be part of the community and where can we deliver unique value? And so where we think we can be part of the community is at the interface level of connecting to BACnet and Zigbee and Wirepass and analog and digital and OneWire, all these different protocols. And we think, according to the XKCD cartoon, that people keep inventing more of these, right? And so our job is to assimilate as many of those as possible and support them. To this point, we hired Coleman Brumley, who is the head of the International BACnet Committee, to lead our BACnet initiatives. But that's on the bottom level, right? How do we connect to the outside world? And then on the top level, we also decided, hey, quantum should be open. everybody should have access to that and it should be an open API. And now we have an open language that people connect services on or use as a digital twin language on their own. We've also decided to open source, do our work in the open on compilers and on introspection and things like that. But on those sort of the core engine of how it runs, I think here you'll just get bound up as an industry that the speed of innovation will not keep up with getting everybody to agree. And so I think we can pick the interfaces into which we're open to everybody else. And then we can innovate as fast as we can inside that, the box that works with the outside world.
Very well. And maybe follow-up question: how do you facilitate the adoption of those interfaces by those emerging companies?
Yeah, I mean, I guess that's. Will we see it from the incumbents? I don't think so, honestly. I mean, maybe, but I've had enough interaction with the incumbents in various ways that, I had a dinner that was planned 2 days ago with one of the head of one of the 4 major automation companies. And then he called me the night before and said, oh, we're being restructured and a bunch of the leadership's being laid off. And I'm like, this is the building industry. It's not like it's going away. You're going through a 3-year soft economy and you can't invest in 3 years to head towards a regression point 4 years in the future. Like that, so I've seen enough of that in the last while that I've sort of quit taking calls because every 6 months, their leadership's different, right? It's just not even worth my time. So I'm not sure that we're going to see
among the big four, amongst the big four.
Yeah, that it's, I'm not convinced that they'll be able to keep themselves glued together. Interestingly enough, I don't see, we're in a unique position that's unusual right now. And I think that has to do with the state of the investment industry 5-6 years ago when we started, that it was not a cool thesis, buildings. Energy was even less cool. And there had to have been a half a dozen PassiveLogics out there, but getting over the hurdles of investment at the time would have been too difficult. And so there's not a lot of, there's some point solutions out there, there's add-on solutions. There's not a lot to choose from of like, what are the new, where's the new players that are like a full stack platform?
How did you make it through the valley?
We made it, well, I think we had a few advantages. So my co-founder had been a very successful startup, but that didn't help. We had access to all the big investors. And I remember to this day, one of the meetings that we had at a tier 1 investment firm on Sand Hill Road. And it was a half-an-hour meeting. It went 2 hours. The guy was super intrigued. And he said, I'm trying to figure out how I sell this to the investment committee. And he said, my partners are idiots. All they understand is click-throughs, which and web advertisements. And we kept on making it through 3 things: our own money, DOE grants, and some committed angel investors who had some prototype equipment in their buildings from us, and we paid ourselves virtually nothing. And then what happened is about 4 years in, all of a sudden buildings became a cool thesis. And then in January,
what prompted that? What prompted that change of sentiment that buildings became cool?
Yeah, it was all of the big strategic players in the building industry realizing that gap, that here technology is taking off in all of these categories, and now they're seeing it in vehicles and they're seeing it in other industrial spaces, and they're like, boy, if we don't start investing in our own space, we're going to be out of business someday. And so about 3 years ago, you saw this influx of strategic investment from the big REITs, companies like Brookfield, who's invested in us, or several of our investors are what I'd call a meta REIT, where they've taken money from a bunch of REITs and then they're investing in technologies to suit the purposes, the goals of those REITs. And so that started really taking off 3 years ago. And then the other remarkable thing that happened, and it was almost to the day that I could recall. So when we first started pitching PassiveLogic, in 2016, we had these energy efficiency slides and people were just like, bury that, don't show that to anybody because that's so uncool. You will not get funded with an energy efficiency thesis.
Oh my goodness. Really, they said that.
They started showing click-through rates.
Yeah. And then
crushing.
Australia caught on fire. And in January 2020, everything changed. And all of a sudden there was articles coming out from these VC blogs. They're saying, climate's the new future. We've got to invest in climate. And it was like a step function from no interest, in fact, anti-interest to interest.
That's interesting.
Sounds promising.
Yeah.
And so there's wind in the sails for all of us?
There's wind in the sails for all of you.
Troy, hold a thought. Troy, 1 second, because we're running out of time, and this is the question I wanted to ask. So as your closing sort of like comment, where do you see our community going? What are sort of like the big challenges that you see we should address as academics, or also in the translation from academia to industry, education? And where are we going? Will we still be, like Gregor said, are we going to meet at RLEM’22, and what we'll be discussing then? So what is your vision, and what should we address to achieve that vision? Maybe closing comments from both of you.
Yeah,
go ahead.
I think so. You guys have been in this space for a long time. I think what we're seeing is going to start propagating down towards you. And I think there's a lot of optimism of the kind of interest in investment and strategic planning that's going on, within the marketplace. And the thing that I wanted to really refer back to at the beginning, there was a question where somebody said, so it's all done. What do we do now? After I give my presentation. And I thought about that for a moment, and I think there's actually sort of an embedded thing there, which is when we started this process, we'd look at a thread and we'd say control, and we get all the way down to what the core problem was. And we'd look at fault detection and get all the way to the core problem, and all these different topics actually all led to the same core problem. And we said, it's really intractable to consider that we're going to evolve our way out of these dumb boxes where they're sitting on the bottom and you're trying to make something smart on the top. That we think that fundamentally that's not a possible solution, that you can't undumb the dumb box, and you can't ever make the thing on top smart where the dumb box is filtering the world. And so I think if I were to interpret what was being said there is there's a lot of things that we've done to reinterpret how it should work that does take a lot of the problems off the table. Now there's a whole new problem set that's worth exploring, and the conversation I've had with Draguna, a week ago, is that I think that some of the baggage of the existing industry has caused us to plan for the future by looking in the rearview mirror. And we need to set new regression points of this is where we're headed, and where the research needs to be, and the public funding and support needs to be headed towards those future goals, because headed towards the assumptions of the past aren't actually helpful. And so I think that's one thing for the people in this meeting to think about is take an optimistic view instead of a pessimistic view that you're going to be straddled with these old clunky VMSs to be plugging in. That okay, let's assume that we've got newer platforms, and let's start pushing our advanced research to intercept that 2, 3, 5 years in the future.
Thank you, Troy. Gregor, your final thoughts?
Yeah, I think my final thought is that we just heard about ESG goals, environment, sustainability, governance being all of a sudden now in the room, and they won't leave, and that's good for all of us here. I think we're seeing a time when the general public is recognizing the importance of buildings as being both a problem and possibly a solution to addressing these goals. So I think that should generate a level of excitement for all of us to keep on working on making buildings better, because they need to be, because they are now, that work on buildings is aligned with what the broader population believes is important for us. So that should also generate an excitement among young people to enter our field. And it should also then hopefully translate to opportunities of our students in the field out there. I hope we can move forward in this community to try new things, and take the steps to convince the stakeholders out there that buildings can do better than they currently do, with and without PassiveLogic's ecosystem installed. But I do want to issue a word of caution. I just want to remind everyone what happened to passive solar systems in the US. They died a horrible death. It's an otherwise sensible technology, but the installation sucked to a very large degree. So no one wants to know about passive thermal systems and solar water heating and all. No one cares about this, and no one wants it. So I think there's the word of caution is let's try to find risk-affine building owners and take them and build a small but growing portfolio of positive news that we can spread, where advanced controls has worked, where the adoption didn't lead to a massive disaster, and that generates excitement in the industry for new I would say in the community of building owners and operators to try new ways. But I think we need to be careful not to overpromise and then underdeliver systems that are just too raw and too immature. And I think that means that sometimes we may have to spend a bit less time on some of the algorithmic developments and really see where is the rubber hitting the road. How do we get into the buildings in a way that everyone feels comfortable and is willing to take the risk at bite sizes that are digestible. So because I think if we can point to a clearinghouse, a database of successful implementations of reinforcement learning, MPC and whatnot, and new approaches that are breaking with the convention, I think that there's a lot of others who would be more willing to follow that group and have the population grow, the population of better buildings that we all want. So that's my.
Those are beautiful words. Thank you, Gregor. Thank you, Troy. Thank you, everyone. So this is the final closing. We made it. Thanks my co-organizers for putting a great program together. Thanks for all the presenters that made it happen. Thank you, the audience, for the discussions, asking the questions, bearing with us through the hybrid mode. Hopefully it was useful and workable. I have one final, two thoughts. One is I would like to hear from all of you, some kind of feedback, if you liked it, if we should do this again, if you had some takeaways, if there are, in the past, if you had collaborations coming out of these meetings, I would like to hear them as success stories so we can advertise these, because we do need to make these events every year and make a case for them. And one is if we can point to successful projects, papers, whatever's that coming out of this. So that would be nice. If you want to be involved more, feel free to submit papers. Let me know. We can bring you into the organizing area. You can help chairing and things like that. So very excited. And other than that, I'll leave you with this right on time, roughly at 10:30 or 12:30 in Boston, wherever you are. I'll thank Troy for staying up late, Gregor for getting up early, and everybody in Pacific Asia as well. Thank you. And we'll put the recordings on YouTube because there was a lot of good thoughts and excellent quotable moments. And then we can rewatch it and enjoy it again.
Sultan, do you mind sharing the chat? I don't know how to save the chat because there's some emails being exchanged, and
I believe the chat will be saved with the recording. But
I cannot do that.
We are recording, so, and I think the text is being saved. I will ask Kingsley to make a screenshot or something of the chat just in case. And then we are also active in the Slack. So you should all have received the Slack join link invite where everybody can stay in touch. It's not super active all the time, but at least you have most people on there if you're looking for someone, and you can get in touch quickly and send an email or information over, or advertise a new paper or some kind of event, so that we keep that active there. And if otherwise, just get in touch with me. Alrighty, that concludes the session. Thanks everyone, and I'll see you in 2023 at RLEM. Thank you.
Thank you.
Have a good day.
Thank you.
Good evening, good afternoon, good morning. Bye-bye.
Forward to seeing you soon, Troy. Bye-bye.
Bye. Thank you.
Thank you.
Bye. Bye.
Thank you, Thibaut. And Greg, show your face.
I think Greg was in car, he was driving somewhere, maybe.
Oh,
yeah.
Greg was driving. Okay, good. Well, he asked a really good question.
Yeah. Kingsley, before you can stop the recording, but before you close the meeting, you can probably just screenshot the chat just in case.
Yep.
Thank you.
Yeah,
and maybe just throw it in the Slack channel, and then we can also share it later.